Be right back.
Wow, David, that NGC 891 shot is incredible.
Isn't that something?
Posted today. Who did that?
The Canada-France-Hawaii telescope.
Oh,
That's one of the telescopes on Mauna Kea,
yeah.
and I always love whenever this comes up because they do such a nice outreach program of shooting bright deep sky objects. I always like to mention this. One time in, I think it was 2012, I was going up Mauna Kea with a group, and we had breakfast with the person who was then director of the CFHT. And I just about fell out of my chair and dropped the pancake or whatever it was, because he was talking. We were going to see the Kex, the 10-meter Kex that are the second largest telescopes in the world. And he said, well, there's certain things that you really can't do that well with a small telescope. Now he's talking at the Canada, France, Hawaii telescope. That's a
120 inches or something, right?
That's a 3.6 meter telescope, exactly.
Yeah.
And these guys were sitting around talking about a small telescope. I just about fainted.
Okay, so during the eclipse, the 91 eclipse, that's where I was with. I was shooting the eclipse with Nova that broadcasts on WGBH. So I was part of their film crew.
Yeah.
And so I'm there for 4 days and 3 nights, no sleep. And I'm going up and down the elevator in the CFHT to get oxygen every few hours. Okay.
Wow.
And it's then I learned that professional astronomers aren't exactly so nice to each other, all the time. So, they were like yelling and screaming at each other and stuff. And so that was that held me a little aghast during that time. But we had some nights, David, where it was sub-arc second seeing. And I was working so hard on my telescopes to get them drift aligned. That at one point they asked me if I wanted to come up in the dome and look at Saturn with the scope.
Wow.
And I didn't do it because I needed every minute that I had to get those 3 mounts that I was we had 35 millimeter motion picture cameras on them, and I was drift aligning. So I don't know how they set it up, or maybe it wasn't actually through the big scope. Maybe, I don't know if there was a refractor next to it. I really didn't even have a chance to go inside the dome and really look at the telescope. So
Sure.
Yeah. Well, guys, can you hear me now?
We sure can.
It's much better,
I'm on my cell phone, so it's I think it's got a better connection right now.
Oh, it is a better connection.
Yes, definitely.
The computer I had, my friends, is the same one that Chaucer used in the 1300s.
Really?
Yeah. Really? Nero used it.
That's very nice. Yes. Now, is your tablet a clay tablet, or what kind of tablet are you using?
It is a fossil turtle that I have.
He wrote the Miller's Tale on it.
Yes, he did. Right on my computer. But it usually works, but today it's not. So I'm using my cell phone. Anyway, it's good to be connected to you guys.
Absolutely.
Yeah, you sound and look much quicker now.
Thank you. And Wendy sends her love to everybody.
Hi,
Good.
Wendy.
Love back to Wendy. We're glad she's recovering quickly.
Yeah, she is. She is really doing nicely. I'm very proud of her.
Good.
Did I miss something? What's been wrong?
Wendy had abdominal surgery yesterday.
Oh.
And but she came over it with flying colors, and she's doing very well right now.
That's great.
So
that's always painful, though.
it's a very painful experience, but she's on the mend. And to celebrate it, it's a clear night. Or
Beautiful.
will be a
Oh,
clear
good.
night.
So did you like the theme of tonight's Global Star Party?
Yes, I had trouble finding an appropriate quote for it, but I do love the theme.
Yeah.
Having trouble finding a quote, I thought I found one. Shakespeare wrote a play called Romeo and the Hubble Space Telescope,
Oh, that.
but I couldn't find an appropriate quote from it. And Tennyson wrote a very nice poem called How Faint Can the Hubble Telescope See? But it didn't seem to be one of his best. So,
No, it wasn't. Yeah.
but I found one that I think you guys might like.
Cool.
They were both a little ahead of their time. Huh?
Yes.
They sure were.
Mm.
If you review the number of expressions that are in common English usage that come from Shakespeare, it's absolutely astonishing.
Hmm.
Yeah, although not a single one about the Hubble Space Telescope and the mirror.
I
problem
didn't see that coming.
Nope.
Yeah. There's a lot of Shakespeare about comets. He's got it all over the place.
You must have loved comets.
Yeah, he did. He really, really did.
Hmm. How could you not love comets? I mean, come on.
It's against the law not to love
Against
comets.
the law. That's right. Especially in
Yeah.
astronomy land. That's right. Mhm. And we got, is it Mariano? Is that how you pronounce it?
Yeah, that's right. Hello,
Great.
hello everybody.
Great. I tried to find a picture of you for an announcement poster, but I couldn't find one. But I'm glad you're on the program. It's awesome.
Thank you for the invitation. Thank you for
Yeah,
opening this door to an unknown community.
yeah,
So-
that's cool. Are you? And Gary Palmer's here with us. That's great. So who we have with us right now is David Levy. We've got David Eicher from Astronomy Magazine, and Chuck Allen from the Astronomical League, and Gary Palmer from Wales and the UK. Really great astrophotographer. And
Nice. So this is really global meeting.
it is very global. That's right.
Okay,
Now,
nice.
are you, Mariano, are you in Argentina, or where are you right now?
Yeah, I'm in Argentina. I'm a researcher for the National Agency from
Okay.
Research, and I'm physicist, and I'm working mostly in solar physics. Well, that's all my work.
I see.
I'm very
Wonderful.
specialized in solar physics,
Wonderful.
and this is my first outreach event, international event.
Oh, really?
I'm doing outreach locally, but
Mm-hmm.
I didn't know about outreach outside, and so this is my
Yes.
first time in this kind of meetings.
Well, you're always welcome to participate in our global outreach program. So it's
Okay, thank you.
it's easy to do
and-
because you never have to leave home. So
That's right.
Mhm.
Yeah, Cesar Brollo always told me about this community, and it was very friendly and nice, and he's always having fun about all the meetings you arrange.
yes.
So he spoke very well about you also.
Oh, thank you. Thank you. So I fooled him. I was able to trick him into liking me. Yeah.
Nice.
And how long have you been doing research like this?
Research, well,
Your solar work.
I got my degree then PhD, then a postdoc, and now it's been like 12 years, I guess.
12
like
years. Wow, long time.
Mhm.
We have people logging in right now. Let's see. We have Billy Beckett is on, Book Davies, Mike Wiesner. Some of these people I know where they are. They're in Arizona. Mitzi Mills is my cousin down in Texas. She's watching. Harold Locke from San Diego. Who else do we have here? Jeff Wise. I forget where Jeff is exactly. And yeah, they're just starting to get settled in here. So.
Oh dear.
Well, I'm honored that your first international outreach effort is with us. That's great.
It really is an honor, and it's a very special thing to have you on our program tonight.
Oh, thank you. Thank you very much. Yeah, it's a great experience, I guess. I'm also, I'm not used to give this kind of talks in English, so I could probably get a little nervous or.
No, you know, we have people.
Better English than us.
We have people from all over the world, and sometimes they're, you know, the accent is really heavy, or they don't have the right English word or something like that. But it's just, you're just talking to friends. That's all. You know?
Yeah,
So,
yeah. I will try to take your advice. I'm talking to friends, so
You are talking.
I guess
to friends.
that would be easier.
It is.
So Cesar just came in, I guess.
Mm-hmm.
Hi, Cesar.
Is Cesar here? There he is.
Hi,
Hey, Cesar.
how are you, everyone?
Good evening.
Good evening. Hola, Mariano.
Hola, Cesar.
Hello, everyone.
Mariano.
Hi,
And-
hi, David.
Hello, where's I'm here on my cell phone today.
Yes, all the way from Vail, Arizona.
Yes.
There's a UFO and astronomy group somewhere in Latin America, it looks like. I share it to them.
I don't know much
I put
about
UFOs first, so they're probably more interested in the UFO than the astronomy. I don't know.
that.
Let's see. So what I do at this part of the program, Mariano, is, you know, I let people get settled in. I start sharing the show to different groups on Facebook, and but we're simulcasting on YouTube, Twitch, Twitter, and a few different pages on Facebook. You know, so.
Oh, Scott, here's a question for you, which I forget. I know that there are live viewers and then people watch it for some days to come in all sorts of different modes, as you just mentioned. Do you
Yeah.
know what the sort of total audience for some of these shows is?
You know, I added up. I added up last year's count. You know,
Yeah.
kind of in aggregate of all the viewers, and it was
Yeah.
over 1 million.
Wow.
Wow.
Yeah.
But do you know sort of per show roughly what it would be?
Per show averages. You know, we run shows every day, sometimes 2 shows a day.
Yeah.
I think at the very low end, it was something like 600 or 700, and on
The
the high
Space
end,
Telescope was
several
named
thousand,
for Edwin
you know.
Hubble, a great
Excellent.
astronomer who did much of his
maybe
pioneering
upwards of
work
10,000.
in the 1920s
Gotcha.
at Mount Wilson Observatory,
Curious.
California.
Or if you
In those
can,
days,
I don't
our
know,
own
from
galaxy, the
whatever
Milky Way, was
ways
considered
to
the entirety of the universe.
the administration.
Nearly everyone,
Because for me, it
even
seems that the
Einstein,
administration, they don't
the
care.
universe had existed
They're just,
forever
it is
in
what
its
it is,
present
and
state, that it was eternal and unchanging. But Hubble would prove them all wrong. He began by figuring out how far away the stars he was seeing actually were.
At the time of Edwin Hubble, it was hard to measure distances. It still is, even today.
It's difficult to know if a star appears bright because it is actually bright, or simply because it is close to us. So Hubble searched for a rare type of star, called a Cepheid variable. Cepheids pulse at a known brightness, so by measuring the amount of light he could see, he could calculate how far away the star actually was. In October 1923, Hubble found a Cepheid in a gaseous cluster of stars then called the Andromeda Nebula. It yielded a shocking discovery.
And when he actually did the calculations, he discovered Andromeda was roughly a million light years away from us, which was outside our galaxy.
Andromeda was its own galaxy.
Oh, there are other galaxies out there, and we're just one of them.
For the first time in history, there was evidence that our universe stretched far beyond the Milky Way.
But then what he did was, we measured the speed of a whole bunch of these galaxies.
Edwin Hubble measured speed by looking at the light the galaxies emitted. He knew if the galaxy was moving toward him, the waves would shorten and shift to the blue part of the spectrum. If it was moving away, the waves would lengthen and shift to the red.
Every distant galaxy Hubble looked at, he saw the light from it being redshifted, which meant everything is moving away from everything else.
And he found the further away they were, the faster they were going.
In fact, the universe itself was expanding, stretching the light from the galaxies. Edwin Hubble had changed our understanding of the cosmos forever.
The whole universe was clearly expanding. And so this was the discovery of the expansion of the universe, which Einstein said, well, that's crazy, right?
The discovery of the expansion of the universe, of course, was a very strong piece of evidence for a beginning. If everything is now expanding, you can run this backwards and see that everything should have started from a certain point or singularity, what we today call a Big Bang.
Well, hello, everybody. You have arrived at the 65th Global Star Party. I'm Scott Roberts from Explore Scientific and the Explore Alliance. And our theme tonight is Lookback Time. And so what is Lookback Time? That's the time that if you think of a telescope or a sight as kind of a time machine, the further away something is, the further back into time you're seeing it. So, if you're just talking to your friend, you're seeing your friend the briefest fraction of a second ago, not in real time, okay? But it feels like real time. As you start to look at stars, galaxies, quasars, they're further and further away, and we can see, hundreds of years back into time, thousands of years, millions of years, and billions of years. And so this concept is something that is sort of startling and humbling to people once they realize their scenario. And anyways, it's the subject of tonight's presentations. Of course, that any one of these subjects could take us anywhere in the universe. And so we have a great lineup of people And as always, we start out our programs with some commentary and poetry from our dear friend David Levy. I'd like to share I've had the opportunity to observe with David Levy on more than one occasion, and it's wonderful because when you're in his observatory, he has artifacts that are in the observatory, like a backlit glass plate of the Milky Way from Bart Bach, and telescopes that he discovered comets with, and all the rest of it. And so you really feel this ambiance as you're looking back into time with David. So it's so cool. And David, I'm going to turn it over to you, my friend.
Well, thank you so much, Scott. And it's great to be part of the 65th Global Star Party. And what I've been trying to do is to find relevant poetic quotations for each of our themes. And tonight's theme, looking back in space and time, I really wanted to see if I could find one that was represented by one of the great astronomers of the past. And I found one in Alexandre Dumas, The Three Musketeers, and the Hubble Space Telescope. And I read through it to find out what he had to say about the Hubble Space Telescope, and I found there was nothing he had to say about it. So that didn't work. I went to a history of Nero, who fiddled during a great fire in Rome and looked through the Hubble Space Telescope on the same night. That didn't work too well. In Memoriam and the Hubble Space Telescope by Alfred Lord Tennyson, that really wasn't a success either. But seriously here, as we try to look at the universe to find out what there is and how we quietly look up at the night sky and look into space and time, I finally found one with John Keats in his Ode to Autumn and Looking Through a Telescope. And that's what I'm going to quote for you right now. Where are the songs of spring? Aye, where are they? Think not of them. Thou hast thy music too. While barred clouds bloom the soft dying day, and touch the stubble plains with a rosy hue. Then in a wailful choir, the small gnats mourn along the river, among the river's sallows, borne aloft, or sinking as the light wind lives or dies, and full-grown lambs loud bleat from hilly bourne. Hedge crickets sing, and now with treble soft, the red breast whistles from a garden croft, and gathering swallows twitter in the skies. Thank you, and back to you, Scotty.
Thank you very much. Thank you. Our next speaker is the editor-in-chief of Astronomy Magazine, a great author, a great friend to many of us, and someone who loves all aspects of science. I think he's very involved in astronomy, but and learning about his upbringing with his father, who was a chemist, and a gemologist, I guess you might call him, and a lot of this stuff rubbed off on David Eicher, and he has embraced it and has shown us the common threads of all of these different aspects of science that make up our universe. And so, David, I'll turn this over to you.
Thank you, Scott. It's great to be with you again, and thanks, David, for such a wonderful introduction, as always, for all of us for this whole star party. I'm going to attempt to share my screen now, Scott, and see if that will work for me.
Okay.
So that I can show some slides again. And what I'm thinking, let me see if I can go into it. Can you see it now? And what I'm going to do, you'll have to forgive me because I'm a week behind. I'm looking back, my look back time tonight for me is a week, because I was planning to show this program last week, and I had a last minute conflict come up. So I'm on the theme of stardust and gemstones still, so forgive me. But this is another little segment of showing some mineral specimens that I've collected over the years, and thinking about how the universe makes substances and makes planets. And of course, things are all ground up and randomized on a planet like this because of all sorts of processes on a terrestrial planet like Earth. But the way substances form in the universe is no accident. They're the atoms that make up these crystals, these gemstones, if you will, are brought together in a very non-accidental way because they're electrochemically attracted to each other and because of the way they form. So tonight I'm going to show some gemmy stones, if you will, a little bit, because these are minerals that are somewhat complex, their composition, and they form in what mineralogists call pegmatites. Now, these are high temperature volcanic basaltic lava flows, and that's where you get some really neat and really exotic and gemmy looking stones in these high temperature pegmatites. And many of these, of course, we've adopted for jewelry over the years, for several thousands of years even. So I will see if I can run this show, and I'll start with and there are a couple of really weirdo minerals thrown in here now for the first time that are not very familiar. So I've added some of the names at the bottom here, but we'll just talk a little bit about a few of these examples because it's amazing. I mean, this is how the universe makes planets. We know that temperatures and pressures and other local conditions would change all over the universe dramatically. But we know that we're discovering thousands and thousands of planets near us in the galaxy and other star systems. And we could expect, because the chemistry is the same everywhere in the universe, we know that through spectroscopy, that similar minerals to these would be forming on other planets throughout the galaxy and other galaxies too. So it's kind of a neat way to hold in our hand what the universe likes to do with these substances. This one you can see is a hexagonal crystal. You can see the top of it there, and there are a couple of other minerals called schorl, the black mineral, and orthoclase, the white mineral, stuck to this. But this is a fairly large crystal of a mineral called beryl, aquamarine, the type of beryl, the coloration and form, and it's a beryllium aluminum silicate, and of course it's one of our favorite minerals to make jewels with. So these are just sort of garden variety examples of the kinds of pegmatite minerals that form on Earth. There are approximately 5,000 different mineral species on our planet. This is corundum. That's a fairly simple high temperature mineral. It's aluminum oxide, and this is the variety that is called ruby. And it's all of these minerals, by the way, they get their color and their sort of appeal for a lot of people through impurities, really. This is aluminum oxide, but it has small amounts of a small number of chromium atoms in the crystal lattice that forms. And that's what colors it red or pink, the ruby. And ditto with the aquamarine, is colored largely by iron impurities in the crystal structure. So here we go. We saw aquamarine. Here's another type of color and of form of the same mineral, beryl, that's called heliodor, and that's the yellowish gem variety of beryl. This again is colored by iron impurities in it and forms it's a very unusual, somewhat rare form of beryl, and many of these good crystals of it come from the Ukraine and from areas in Russia, as does this one. Now, this is a very common group of a sort of a jewel pegmatite, if you will, called tourmaline. That's a big family of different types of minerals that are all closely related. This is a somewhat complicated one. It's a sodium, lithium, aluminum, borosilicate hydroxide. So if you want, I can email you the chemical formula for this one that's just about as long as your arm. It's a pretty complicated one, but these tourmalines are very attractive, and you can see that the chemistry of the hot fluids that were flowing into this pegmatite rock and slowly cooling and crystallizing over perhaps a long, long time. The chemistry of the fluids changed as this crystal was building. And so it went from this very dark green on one end here to a sort of a translucent red-orange. So we see all sorts of interesting things in the way that crystals form. This is a weird one here. It's called Yeremievite. That's a very unusual bluish mineral. That's an aluminum fluoride borate hydrate mineral. This is from Namibia. It's a very rare mineral. It forms transparent or translucent bluish crystals that are pretty like this. It's quite rare from a small number of localities, and it's a complicated mineral that gets its color probably from boron atoms. Here's one of our jewelry favorites ever since it was popularized and discovered in huge quantities in the 1950s and 60s. It's a mineral called zoisite, and this is the gemmy bluish purplish lavender form of it called tanzanite. And it's actually trichroic, these crystals, and that means that as you turn this crystal in two axes, if I could show it to you in real time, you'd see it changes color. It goes from a very deep blue to a lighter blue to a kind of lavender purple because of the refraction of light through the crystal. So it's a very unusual, complicated chemical. Again, this is a calcium aluminum silicate hydroxide, and it's probably vanadium atoms that are coloring the tanzanite. It's deep gemmy blue purple. This one is another sort of gemmy, interesting mineral. This comes from the famous Jeffrey mine in Quebec, Canada, and it's called Vesuvianite. It's named after its discovery locality was Mount Vesuvius, but this is sort of the gemmy best locality for it is in Canada here. This is a calcium, magnesium, aluminum silicate hydroxide. Again, lots of stuff going on chemically here in these high temperature pegmatites that crystallize, and you can see the color ranges here from a number of impurities to purple to lavender to green to sort of a yellowish. So again, it gives us lots of pretty colors. Here's yet another form of beryl. This is an emerald in its native rock from Colombia, which is where most of the great emerald crystals come from. This is beryllium aluminum silicate, and is probably colored, its rich emerald green color that we name after emeralds comes probably from a combination of chromium, vanadium, and iron. So it's somewhat unusual to get a beryl crystal, an emerald crystal in a big chunk. This is a fist-sized chunk of rock, because normally they're extracted and the miners, hide them and run away and go after each other, and there are nasty things that happen to make a big profit from these stones and get them outside of the country. So this is a little bit of an unusual specimen. Here's another weird one that is named after a locality where it was first discovered in North Carolina, and this is from that original locality called hiddenite. This is another form of spodumene, which is a complex silicate. This is a lithium aluminum silicate, and it's from the Adams Hiddenite mine that is an old mine in North Carolina. And again, it gets its sort of gemmy greenish color from iron impurities. And then I finish off just with a couple of the tourmaline group, and you can see this nice crystal structure. These are favorites. Also, most all of these crystals, like tourmaline, are very dense. So they're also good as far as jewelers are concerned for cutting and for wearing and things. They hold up very well. They're hard minerals, and there's a huge range of color with this tourmaline group. This most common kind of tourmaline used for jewelry is called Elbaite, named after Elba Island, Italy, where the original locality discovery was from. But you can see again the chemistry of this fluid changed over time as this crystal built up with more and more atoms that are attracted and connect to this original seed, and it went from a sort of a lavender and pink up to a sort of a greenish translucent color. And then just to finish with one more tourmaline, here's a somewhat unusual one. This is from a famous locality in Brazil that's called a watermelon tourmaline. And it forms this sort of core of a pinkish color inside and then a sort of a greenish rind, if you will, on the outside. So there's just a very quick snapshot of the kind of gemmy minerals. Forgive me, I'm a week behind on the stones and the gems, but I'll catch up next week. And that gives you sort of a quick snapshot of the variety of the kind of high temperature, so-called pegmatite minerals that form here on Earth, of many, many, many dozens, just a few examples there. And again, just to finish, Scott, these are a couple of latest books, and in the coming week, I'll have some new book projects to talk a little bit about at some point soon here. But Galaxies, Cosmic Clouds with Brian May, and then of course the recent issues of Astronomy that are rolling out as well. Check those out if you will. Give us feedback on these. We always love to hear from the whole crowd of the amateur astronomy world, such a wonderful bunch of people. So thanks again for having me tonight. Scott.
Thank you, David. Thank you. Hey, I was curious, I mean, with such an incredible collection of minerals and gems and stuff that you have, you must belong to some group, maybe like the Gem Society or something like that. Do you partake in any of the organizations that focus on these things?
I know a bunch of people who are in such organizations, and I haven't done much. I've been busy enough with astronomy and with some history as well in the past, that I haven't done much organizationally in the world of mineralogy and rocks and gems. But I know a huge number of people who are collectors and who are dealers, because in the old days when my father John was out in the West, his first trip out there to go to gold mines and silver mines was in 1926, when he was 5 years old, up until the time of World War II, when he was out doing a lot of stuff in the West. You could self-collect. You could go out and go to localities and collect.
Yeah,
that's all gone because of largely the danger and lawyers worrying about people falling down mine shafts, and so on. So those things are really all closed up and off limits. Now you need to collect minerals through dealers at the Tucson Gem Show and at the Munich Gem Show and other places like that. So you get to know a huge number of collectors and of dealers of minerals who are really experts on this stuff, getting into a field like this. So I know lots of people like that, although I'm not really active in a society.
You're just so good at giving these presentations and making each gem sound like a treasure, which it is, and so I'm just real impressed with the presentations you've given on these things, and it makes me want to get into it myself, so.
Well, thank you.
You wanted to say something,
May I make
David?
a comment?
Yeah.
Yeah, thank you. I know that I really enjoyed what you had to say about the minerals possibilities on other worlds, and really enjoyed seeing what of these minerals might be found on other planets. And while I was listening to you, I was able to find out that you really did want a quote from Alexander Dumas this time. And it turned out that he did write a book called The Three Musketeers, David Eicher's Minerals, and the Hubble Space Telescope, in which he says, I'm going to try to find this if I can. I thought I had it here. And it's right here. And Dumas writes, in the real The Three Musketeers, on what was D'Artagnan thinking that he strayed thus from his path, gazing out at the stars of heaven, and sometimes sighing, sometimes smiling. I just wanted to add that to our global star party tonight to see where we go. Thank you.
Very nice.
Thank you, David. As always, you
ties it all together
with inspiration. Exactly.
Wonderful.
Well, we never know where these global star parties are going to be taking us.
That's right.
And as we
Yes.
found out from David's talk, but they're taking us far afield. So it's really interesting to see where this goes, as Dumas said so well in The Three Musketeers.
So I wanted to, I don't know the answer to this question, and I'm sure that one of you can give an answer. For each hour that passes here in the Global Star Party, how far into around our sun or through our galaxy do we travel each hour?
Oh gosh, a long way. And I'll have to check. I don't want to give an answer that's wrong. When we're done with me and we go on to something that's better here, I'll check and I'll come in with a number later. I would like
to, people, I mean, we're sitting down, we're watching this on our computers or whatever, but we don't feel the movement of anything, right? So
no. And that's again thanks to our Uncle Al and relativity and frames of reference. Of course,
that's right.
We are moving, but I hate to venture guesses.
483,000
without really knowing.
5% of the network, right?
480,000 miles per hour.
480.
3,000
That's
miles
galactic
per hour.
orbital velocity. Earth's orbital velocity around the sun is about 30,000 kilometers an hour. And that, of course, is the average impact speed for meteorites. Or
as we're going around the sun.
Right.
I think he was talking about orbiting the Milky Way.
Yes, I am.
Orbiting the Milky Way is much higher velocity. But
That's what I was referring to.
But then we have our galaxy moving towards Andromeda, right? So
the great attractor, and Andromeda and the Milky Way are both moving toward each other. But even the rotational velocity around the galactic center, that's a pretty impressive number.
It is.
Because since the origin of the sun 4.6 billion years ago, we've orbited the center of the Milky Way about 22 times.
Oh, wow.
Even at that velocity. So that it's a long way around that circle.
Somehow I felt like we've been here before, and we have. So
one of the things we can say is that over the last half hour since we've had a global star party, we have traveled virtually from most of the way from Jupiter to the Earth, and the speed of light. So that just 1/2 hour, we've traveled almost from Jupiter to the Earth.
But if you want to be pedantic, you can even say with respect to each other, we're not traveling at all.
That's true. Yes. I was going to say, Karim, before you said that, I was going to say, geez, now I know why I'm so tired at the end of the day.
Yeah, you're getting whiplash.
Traveling at all relative to each other.
That's right. That's right. Well, it's kind of that same feeling when you've been traveling on a plane all day long, so, right? You've just been riding on this planet nonstop. So there you go. Well, that's great. Okay, so next up is Chuck Allen, who's given many presentations here on Global Star Party as well. He will be presenting the questions from the Astronomical League's executive staff and presenting not only the questions, but also giving the answers to last week's questions for door prizes. And so we're very happy to have Chuck Allen with us. And Chuck, I was trying to remember, do you remember the number of people that watched the virtual Alcon event that we broadcast together?
I think you indicated it was 79,000 total views.
Okay. Okay.
Yeah, which is incredible. And I think we had a glitch. We couldn't get on YouTube, so it could have been more. There was some problem.
I don't remember if that was the reach or that was the video views, but one number we never get to really quite capture, and I have to guess at, is that we are on the homepage of cloudynights.com. And I know that they have a tremendous amount of traffic that visits that. So if you're watching on Cloudy Nights, we're very happy to see you and glad that you're tuning in. I know there's also star parties that are happening really soon and some events. So we've got Okie-Tex, which is coming up here in October. We have the Heart of America Star Party, which I'm going to give a virtual talk at on the 8th of October. And we have, we're going to be kicking off with the Night Sky Network and NASA, the International Observe the Moon Night. So that's going to be very cool as well. There's all kinds of other things going on around the world as far as events go and that type of thing. I'm just touching on some of them, but it is a great time to be involved in amateur astronomy and to do outreach on any level in astronomy. So, all right. Well, I'm going to turn it over to you, Chuck, and thank you so much for doing this. And we very much are honored to partner with the Astronomical League on these things.
I think that's my line. Thank you. And I'm going to start off by sharing screen here. And let's see here. These pictures are from 3 female members of the Astronomical League who participated and won the top 3 awards in our first Williamina Fleming Imaging Award. Molly Wakeling, who will be, I think, a guest later on tonight. This was one of her contributing images to her first place finish in the Fleming Award. This was one of Lynn Peterson's contributions, which earned her 2nd place. And this was Terry Mann's, one of her auroral shots taken from near Fairbanks, Alaska, which earned her 3rd place. And the reason I'm showing these is because Scott Roberts can't do enough for the Astronomical League. He's saved our National Young Astronomer Award program by stepping forward with major telescope awards for our winners. He's supported NIA for 30 years. He's provided us access and a presence and has provided the door prizes to the league here on the Global Star Parties. He's also, of course, hosted our virtual convention, which gave us a tremendous opportunity to meet with our members again, despite COVID. And now he has offered to sponsor the Williamina Fleming Award. And Scott, I just want to express my appreciation to you for yet again stepping up and helping us. Thank you so much for that.
I think it's great that you guys even thought of the award, and you know, we hope that women around the world can get involved and show off their skills in astrophotography. Will the winners? How will the judging, or I don't know if it's all been completely worked out, but how will the program run?
There's still a couple of things to be ironed out. Let me stop sharing for a moment. We're still looking at whether we have categories. Terry and I talked about this yesterday. We don't want a situation where one person wins all 4 or 5 categories, for example. So we've got to work that out. And we also have a problem if we have people entering multiple categories. If we had, let's say, 12 people who participated, they entered all 5 categories, we'd have 60 submissions that we would have to juggle, which would be a little bit difficult. So we're still working out those bugs, and we hope to have that all sorted out by the end of October. And we're not accepting any applications until after January 1st. Okay. So we'll get that all worked out with you and with Terry.
Yeah.
So everybody's happy.
Well, I'm just here to support. So, you know, you guys know how to run an awards program. So
okay.
I'm just happy to be part of it.
Thank you again, Scott. It means a great deal to us, of course. Okay, back to, can you see that okay?
Yes.
Okay. Well, I'm going to have to stop
sharing. Mann's.
Yeah, it's not advancing. Let me try this again.
Okay.
Okay. Well, this is strange.
Maybe you want to try just sharing your whole desktop and then bring up the app.
Yeah, let me try.
Sometimes Zoom is a little quirky.
Yeah, it's being quirky now, that's for sure. Let me go back to the start here. There we go.
There we are.
Yeah. Okay, as we normally do, we like to remind everyone, especially those joining the Global Star Party who are new to astronomy, that there's a great danger out there if you attempt to observe the sun without taking certain precautions. And among those precautions, and this is to preserve sight that is very precious to all amateur and professional astronomers alike and to all people. And that is never observe the sun without professionally made solar filters that include energy rejection at the front end of the telescope, not those that would be mounted on the eyepiece. Don't leave a telescope or binoculars unattended in daytime where children might attempt to acquire the sun with it. Never use eclipse glasses or viewing cards to look at the sun through binoculars or a telescope. They're not intended for that. They're intended for simply looking at the sun through the eclipse glasses. And you want to make sure you have certified eclipse glasses that meet international safety standards. You have local astronomy clubs who have very skilled solar observers with the proper equipment, and they can help you out with ways to do it safely. Okay, the answers from GSP 63 held last week. The first question was, the moon always keeps the same side pointed towards Earth. However, viewers on Earth can see throughout the year about 59% of the moon's surface. This is due to the phenomenon of not libation, certainly, not vibration, but libration, which has to do with the fact that the moon's rotation occurs over an elliptical orbit, and therefore we get to see a little bit more of the moon's surface. Wednesday is the autumnal equinox, when the sun crosses south, crosses the celestial equator moving south. In what constellation, moving north, south. In what constellation does the sun shine? And the answer is Virgo. Okay. What is the name of the small constellation between the western edge of the Great Square of Pegasus and the star Altair? Represents the shape of a dolphin, and that's the constellation Delphinus, and it's seen right here. Okay, correct answers from GSP 63. These names will be added to the door prize list for the end of the month. Barbara Harris, Josh Kovach, Billy Beckett, Andrew Corkle, and Adrian Bradley, Israel Monteroso, Neil Cox, and Cameron Gillis. Okay. These are the questions for tonight. Again, your answers need to go to secretary@astroleague.org, at secretary@astroleague.org by email, please. First question, this is the closest star to the sun. Which of the following does not accurately describe it? A, it has a planet. B, it's a red dwarf star. C, it's 25 billion miles away. D, it orbits two larger sun-like stars. One of those is not correct. Okay.
Good question.
We'll let people look at that for a few extra seconds. All right, I'm moving on now to question number 2. When the moon is at first or last quarter, tides on the Earth are at their smallest. What are these tides called? Neap tides, spring tides, diurnal tides, or ebb tides? Okay, and finally, question number 3. John Glenn was the first American to orbit the Earth. What rocket seen here propelled him into orbit? Was it a Redstone, the Jupiter C, the Vanguard, or an Atlas? And that will do it for tonight. I would like to, however, invite everyone to join us for the Astronomical League live event on October 15th at 7 p.m. Eastern Daylight Time. I believe, I can't read that. Does that say EDT, Scott?
Let's see.
I can't, it's blocked by
Eastern
the.
Daylight Time. Yeah.
Okay, thank you.
Yeah, I see it. EDT right at the top.
And
Yes.
we have a number of programs set up for that evening. David will join us with Celestial Incantations. John Goss wishes to have his program called The Master of Lunacy, a name which may stick. Terry will be giving us a program on Aurora, the soul of the night. Carol Orge, our president, will be joining us, and Barbara Harris will be talking about algal. And Molly Stewart Adams will be giving a talk on passing between the worlds under October skies. Astro Bob will join us with a program on black holes, where matter goes to die. So I hope you'll join us on October 15th. And once again, Scott, thanks for everything you do for us, and thanks you for the time for doing these questions tonight.
Thank you. Thank you so much. That's great. Okay. Up next is Dr. Daniel Barth. Daniel has been a friend for a very long time. We knew each other back in the day in California when he was working at Scope City and I was working at Mead Instruments. He is a powerhouse of STEM teaching. He is involved, although he's taught science for a number of decades to students of all ages. He is now teaching educators how to teach astronomy in the classroom. And he's written a book called Astronomy for Educators, which we talk about each Monday on a program called How Do You Know? And Daniel's a great guy to, talk about anything to do with science, but he loves astronomy, and he loves to get his students hands-on with telescopes and equipment and to learn the sky, but to actually learn the mechanics of science behind all that. And so, and those concepts that sometimes it's very difficult to wrap your head around, Daniel makes it clear and makes it easy to understand. And so, Daniel, I'm really glad you came on Global Star Party. I know he is in high demand, and as being a professor of astronomy and doing our shows as well on Mondays. So, I'm going to turn it over to you, man.
Thanks, Scott. It's very, very kind of you, and it's really nice to be here on Global Star Party. I do enjoy astronomy and teaching astronomy. I've taught astronomy for about 40 years, and now I'm training young teachers. The interesting thing, almost 40 years of teaching astronomy, about 7,000 students have come through my classroom over all those years. 8 years here at the university, my students will probably reach 300,000 to 400,000 students of their own over their careers. So this was, although I miss teaching science a lot, this was a way for me to have a bigger footprint in astronomy. I worked a lot to make astronomy the fourth core science. That's been kind of a goal of mine for a long time. Physics, chem, biology, astronomy deserves its place as the fourth core science. And more states and school districts are doing that. It's really interesting. We take young teachers out and we show them that astronomy can be exciting, it can be fun. We tend to focus on short 15 to 20-minute activities, something you can do really quickly. I try to stress to my young teachers that when they are teaching, we're not here expecting a mastery of astronomy principles. We're expecting engagement and involvement in astronomy. And so I take them out and we do things. We take binoculars and we explore the southern Milky Way, and they chart the things they find. And then we look them up on things like Starry Nights or Stellarium and go, oh, hey, you discovered the Lagoon Nebula with some binoculars. And they feel like they've accomplished something, which they have. We do all sorts of fun hands-on things. One of the fun things we've done on our program together, Scott, we've had students over the years, and students would come up, set up this wonderful telescope, and some punk teenage kid would come up, yeah, it's the moon, I've seen it. And so I was always very frustrated with that. And I did some research and I found out Young people today are bombarded with tens of thousands of images every week, more than 10,000 images a day. We have our smartphones, we have our tablets, we have our computers. And so I said, okay, let's bring some knowledge to the telescope. And so I taught my students to sculpt a little lunar landscape out of clay. So we would make maria and craters and rills, ejecta, mountain ranges. And after they had created all these with their hands, then going to the eyepiece, then they look in, they go, oh, I see a maria. Oh, look, craters. Oh gosh, that one has a mountain in the center, just like you said. Oh, look, there's shadows. And they get very excited. They are discovering things they've created. And this hands-on engagement model, Scott, the most wonderful thing, it works with students of all ages. It works with students irregardless of what language they speak at home. Because if I'm saying, here, follow me and make a model of the lunar landscape, every child's doing that in their head in their own language. And then afterwards, as teachers, we give people the language that they need. And David is involved in this, and David is involved in this, you're involved in this. We give people the language they need to express what they've learned. Because we're all smarter than we can express. No matter who we are, what age we are, how advanced we are, we all know things that we struggle to express. And so really, I try to train my young people that their job is to help people not only learn new things, but express what they know. And it's really been gratifying. Astronomy for Educators is now serving about 500,000 students worldwide, which is just stunning to me. It's just amazing. And I have a new book coming out, Star Mentor. It's in publication, it's in press with Springer. And so we hope that will be out in the spring. But I'm really hoping that people who are joining us for Global Star Party will drop in on the Monday How Do You Know show. And sometimes we do hands-on activities. Sometimes we get pretty far out. We did quenched galaxies on Monday and talking about primordial galaxies that have run out of gas. And why, for heaven's sakes, if they existed a few billion years after the Big Bang, it should have been a very compact universe full of gas. And so why did these galaxies run out? So sometimes we explore mysteries, and other times we go ahead and we help people discover ways to understand and to share. And that's the real victory for me. And I get emails every once in a while. Somebody say, hey, I saw your show. Hey, I was in your class. And now I do these things with students or with my children. And to me, when we see evidence that the astronomy, the love we share, is passed on to another generation, I feel like that's a victory, that's a legacy. And certainly Explore Scientific does that with equipment. I do that in my classroom, and together it makes a very powerful and transformative thing that we do together. And Global Star Party is part of that. And 65 episodes is just astonishing. When you first started doing this, Scott, I'm like, oh, this is going to go like 3, 4, 5, and then we're going to stop. And here we are at 65. And it's stunning to me. The thirst for knowledge. And you and I have talked about this, Scott. When someone purchases a telescope and you go and set it up, if you're not hiding it, it's a party in a box. If you set your telescope up in a parking lot, on a sidewalk, people show up. Come to you. People come to you and they say, you have a telescope. You must be smart. I want to know things. Hey, can I have a go? Is this the moon? Can you show me a planet? Teach me stuff. They see you as someone who's in the know. And I like to help people learn to become the mentor they can be, to pass their passion on to another generation. So our hobby continues to grow and our passion is shared with more people. And it's a wonderful thing we do.
And it's something that gives us a lot of energy when we do it. So
it does.
That's how you can do 65 global star parties, because it is an outreach event. And
it is.
All of my friends that participate on this are are, they are charged up by it as well, and it gives them a platform to share their experiences, their knowledge, their enthusiasm, their passion. It's infectious, and it's beneficial. It's beneficial for the audience listening to it. So
It is indeed.
yeah, thank you, Daniel. That's awesome. Okay,
I would like to add my thanks to Daniel. I was very impressed with the idea of the feeling of looking through a telescope. It's not just data, it is emotion.
It
I
is.
think Daniel really spread that out and really hit the nail on the head with that. Thank you, Dan.
Thank you. I appreciate that a great deal. And it's a passion, and my students come out, and they come out here to my ranch. I have a little hilltop. People in California would call it hilltop. Here in Arkansas, it's a mountaintop ranch. But people come out to my ranch here in the Ozarks, and we have a nice, relatively dark sky site. And I have students all the time. Wow, I thought this was going to be a drag, and it's lots of fun. I had a good time. I'm telling my friends, and that kind of thing to me is the best victory, because my students are telling someone else, this is really cool, you should try this. And the idea that we can share with passion, and we can get somebody to look into the eyepiece and have an emotional experience. Because if it's just an intellectual experience, we're not going to capture the next generation. But when it's an emotional experience, then indeed, and I have students all the time. We've been looking at Saturn. Oh my God, is that the rings? Are those moons? Well, let's document them and check. And we find it was a moon. It was a moon around Saturn. It's 1 billion miles away. And I've seen it. And we looked the next week. It's in a different place. Oh, it's orbiting, isn't it? It's orbiting. I'm going, yes, it is. These people are recreating in their own heart the same kind of joy and passion that Galileo had, that Hubble had. And they're not doing it in a solitary way. They're out with friends, they're out with fellow students, and they're going to carry that passion into their own classrooms in a few years. Some of them are already doing that, and it's really exciting to get invited back. Hi, this is my professor, and we're doing astronomy. Here's the guy who taught me, and the little yay. Having a bunch of little 10 and 12-year-olds clapping and applauding your arrival just makes you feel like, I'm a superstar. It makes you feel amazing. And you get to see their engagement and their joy. And it's such a wonderful thing. So, and I get paid for this. So
even better.
That's a bonus.
Even better. Okay. Well, thank you. Thank you, Daniel. That was awesome. Thank you. Up next, we go all the way down from here in Arkansas, where Daniel Barth and I are, all the way down to Argentina. So I always like countries and states that start with the letter A. And also we're in the Americas, right? So it's very cool. Cesar, thank you for coming on. Are you there?
Hi, Scott. How are you? Hi, everyone. Hi, Karim. Hi, Gary, Scott, Mariano, David. Well, David, the two Davids.
Gary Palmer.
Hi, Mariano, too. Yes. Daniel, I am not from the sea today, from the seaside. I remember the first time that I know to Daniel Barth, that is a genius, a great lecturer, professor. I remember when I present the eclipse from Las Grutas in Argentina. And I remember that I had in my bag, in the place where I'm from, transmitting the bones of the whales, was a great place. It's incredible that it's near to 1 year ago. Tonight I present that I had the great experience with my group, astronomy group, that it's Bella Vista al Cosmos. Santiago Mayese is the leader of the group. Is an astronomy group that work in the restoration of the San Miguel Solar Observatory, and we work a lot in many works to repair mechanical optics telescopes, domes. We are searching a lot of different materials to complete making the work in the works again, the things, something that tonight we are talking about, the returning the time. Well, we are working in taking time, looking time again, this observatory, because we think that it's great material to, of course, educational or researching, of course that my college, but it's not an optician, it's a great physicist, a solar physician and researcher, Mariano Poisson. He can talk much better than me about these interesting things. But I have some pictures from the event that last weekend, Friday and Saturday, where we present to the people in live again, knowing a Zoom was incredible. See people again from more than 1 year to 1 year, I think. Let me share the screen if I can share this here. I don't know how work. You told me if in the same. You can see the presentation now? Yes. Okay. Yes. Really, the start of this event was a telescope that Santiago Mayese told us, okay, we can move the telescope. The observatory have a telescope that is a refractor for campaigns to move. It's not a telescope that like another ones that put in the seat, with the pyre, have a pyre. But they 120 years ago, they thought that a telescope for to go, to a place to show, to investigate something or make a travel with a telescope. Well, this telescope was 600 pounds weight, car-size telescope, and this was the telescope that we used last weekend to show to the people. 120 size telescope, 5 inches refractor, achromatic. We share with the people this image with this telescope, and was wonderful, very sharp image of Jupiter and Saturn. Well, here you can see we start to assemble our stand in a like it was like a fire of San Miguel history, and the major invited us to put on stand talking about the history of San Miguel Observatory. And here you can see the old telescope that we can put in the place. And well, the first thing that I can make was clean the optics and the mechanics with another members of the group that we work together to restoring in the morning, previous to the evening, where we later showed to the people image of Saturn and Jupiter. Well, here is a part of the stand. Here it's very nice because it's a fire in a road that is a running road or bicycle road, and they put this in 3 blocks. The fire we was in a extreme of the road, and the people walking, and of course that we receive later. You can see a lot of people watching the all people told us, okay, we can see tonight the moon. No, Jupiter. Really? Well, yes. and of course that we have a great connection with the people. We start to use for our staff of Saraco, Optica Saraco, this Maxutov, Cassegrain Maxutov 5 inches telescope from this brand that maybe really was amazing. Really, Scott, I need to say that people from Jingo Optical Company and your this is really something that I saw maybe from the. I am in the business more than 30 years, and I tried a lot of Maxutov telescope, and in this size, I never seen so with really details, very nice, and contrast in the image. It's a wonderful optical tube assembly that really we enjoyed in the night.
Thank you, Cesar.
Really it's a real thing that I tell you, because it's great. Try something that really work very well. We use Yaxis 100 mounts too, and really we had a lot of fun with the people showing different objects in the night. And here you can see we was putting in a table a lot of meteoritos. Here you can see maybe 2 meteoritos that was facilitated by Jorge Rusansky, that is a member of our group. Is a genius.
They're really large. They're very
yes. Come on, we moved that meteoritos 100 kilos. 100 kilos, near to 200 pounds.
Wow.
We work a lot. My back was really, we feel it, this meteorito, the power of the meteorito. Yes. Here, this man is Santiago Mayesi, working and assembling the microscope, the binocular microscope, to see details of. No, the people was amazed because, oh, come on, I can see a real meteorite, or see by binocular telescope, microscope, where you say, oh, come on. And here is in the David Eicher style, we made a lot of 4 different minerals to show to the people, because it's like something that I thought in David Eicher, because David Eicher is a genius for that about minerals and crystals. I remember last Friday. Oh, come on! I need to show that we showed. Crystal and minerals.
So all of those samples are meteorites.
Yeah.
Wow.
This one are 2 meteorites, and this one are minerals and
minerals.
crystals.
Okay.
Yes. I don't remember. I don't remember the name of because maybe Mariano remember, but I don't know. I don't remember the names of the minerals. Well, here another thing to be proud, because it's we use 14 millimeters of 82 series degrees field of view eyepieces, and really were beautiful, because you know, when you have a 120 years old car size telescope mixed with a new technology, Gasberg eyepiece, it's beautiful. I love this kind of because you put together a lot of years and all work properly again, and it's beautiful.
Yeah.
It's really.
I like the way you put that. That's beautiful. It is.
Yeah. Yes, and you receive all the slide that, because well, we maybe if you point maybe to a galaxy, but it's something that the question of times when you receive away from the space, and you think that you have a 100 years old telescope, and they say, come on, it's nothing for the time of the space, but it's magic when you have an old instrument that is returning from the past and working again for the people. The people say, oh, the kids, oh, come on, was a beautiful experience. Two pictures more for the, yes, what they was the dealers, Antigua Casa Oliva, they sold the telescope to the observatory, and here you have, yes, the number of 75. Only I cleared the glasses in the first surface, because I need to disassemble the two lenses and clean special altogether. But only, of course, I don't have time to clean the entire objective, but I clean only the dust, you know, with air. I made a half hour working to one surface, and the telescope worked beautifully, and really we had a lot of fun, and the people enjoy it. Here, well, you have the first one that, you know, when you have by the first time starting the fire, and some people coming and say, okay, I have Jupiter now in the dusk. Was my first view of Jupiter for me was, come on, I can see with a kind of details that I surprised like a kid too, really.
Yeah.
Here do you have a panoramic when the people start to come in a lot. Of course, that the people, comparing with another fair 2 years ago, the people was more, you know, they had more care of don't have a lot together. The people use a mask. Was nice, because the people was very respectful about that. Really, the entire night we enjoyed a lot with the people talking about, you know, when the kids say, when the people say, what are you watching? What I am watching, sorry with my English, and the moon? No, Jupiter. Because where you can see the moon in the sky? No, well, it's a planet. It's this star. It's like, you can see like a star, but you can see a planet. Wow. And the face of the kids, come on. It's, you know, it's amazing. All people too, come on. It's coming a lot of people. Maybe, I don't know, maybe 400 people.
Wow.
Saw by telescope. This was only the Saturday, and the Friday, and the Saturday Santiago returned and with his brother Agustin Mayese, they show to the people with a solar filter a lot of a beautiful image from the sunspots. More people. This is fun because we don't have more altitude for the Bayer, because you can change the altitude for the Bayer here. This is Agustin Mayese, and they needed for the kids were wonderful.
Yeah,
but we changed
for little kids.
Absolutely, yes. The kids was happy to have a telescope very big for
Huge.
them. Yeah, beautiful, really beautiful. Come on, this is 120 years old telescope. It was amazing. Well, all night we received people to watch that, more people. And here we have our expertise in the group. I don't have a picture of his face. What maybe we can invite him from next Global Observatory. He's Fernando Ricardini. Fernando make a great pictures of planetary pictures.
Yes.
And when he saw the telescope, we started to use the telescope for visual for the kids. He told me maybe we can project the Jupiter Saturn in live image. And come on, the live image was incredible. The video in live video was incredible. And I say him, Fernando, please took a short video, record a short video to later make a picture of these planets, because are incredible. The scene was really good, and the optics quality of the Maxutov was. He told me, "Wow, come on! I need to try this." It's incredible. He have a 7 inches Maxutov, and he told me it's very similar. It's very similar. And
big compliment.
Here you can see Jupiter.
Wow.
By Fernando Ricardini. He's the author of the picture.
Wow.
But he told me, yes, he told me I can use, I took only a little the wavelets, but it's the same later I tried I have a video, I think, of this, and you can see the video. I never seen a live video so clear of Jupiter and Saturn.
The seeing must have been incredible. That's amazing.
Yes. I have Saturn here. Was really great. But we'll try again with this telescope to make a more clear picture, because we have a little, of bad polar alignment, but really we enjoy it a lot. But especially in here do you have it in the Saturday with Santiago Mayese, sorry. Showing to the people the solar image in the same fire, the second day fire, was really a beautiful event. Well, here you have the Maxutov for visual use. Was wonderful.
Thank you. Wow. Very good, Cesar.
I
felt like I went to your star party. That's great.
Yes. It was a fire, like a star party, because the people, when you have in a star party, sometimes you have a lot of people that they know how about telescope and talking about it's amazing. But when we are in a fair where the people coming and say, don't expect what they can see from the sky or by a telescope is great, really.
Wonderful.
Thank you.
Wonderful. Thank you, Cesar. Cesar, you have brought on several amazing astronomers onto our program and introduced us to some incredible people that have inspired our audience. You know, and you're bringing on someone new, and
Yes.
we had just a short time to talk to him, but could you do a proper introduction for us?
Yes, well, it's a pleasure to introduce to Mariano Poisson. Mariano is a researcher. He worked in solar physics. We in the group Bella Vista del Cosmos and in the Observatory San Miguel, really, we are really lucky to have a science man, because he guide us to everything about the ideas of the how we can work properly with the huge observatory. And we are really proud, and really we feel lucky to have to Mariano Poisson, because he's a very good researcher in solar physics, and he's very generous. He's a great man, because he talked to the people in the fair, in the star parties. He's explained a lot of things about the sun. It's really we feel lucky to have to Mariano in our group and in the observatory. Really, I'm really proud to know him. It's real. Okay, Mariano, todo tuyo.
Okay, thank you very much, Cesar. I would like to thank you because you introduced me into this large and interesting community. So I know it's my first day here, but I'm sure it won't be the last day.
All right.
Not
That's
the
the
last
right
presentation,
attitude.
I hope. Yeah. Thank you very much, Scott, for giving me this space just to present some things we are trying to do here in San Miguel with Cesar and the group of Bella Vista del Cosmos. So if you let me, I can go directly to share my screen. Let me see. I don't know if
Yeah,
I'm
it's
presenting
starting.
now.
Let's see. Just give it a moment here.
Mm-hmm. I think it's freeze. It's not working.
Just give it a moment. Your voice and video are excellent. So,
Okay, I will try again.
Yeah, try again.
Yeah. To be a part of this group, you need to have problems with sharing screen. Everyone, it's something like our flag. Come
That's
on.
right. It is our
Yes,
flag.
feel like
It's a rite of passage.
If something hasn't gone wrong, then you can. That's right.
Yeah,
you can
yeah.
belong.
Yes.
Yeah.
If you, Mariano, if you have problem to share the screen, you are part of this family.
Okay, good. I think
There we go.
it.
All right.
There we go.
There you are.
You can see it. Okay.
Yeah.
Great. Okay, so I will continue talking about the San Miguel Observatory. I think Cesar had a few lectures before or presentations. So I will talk about a little bit about the sun, proving that the astronomy is not only it's a full day job. I mean, there are many interesting things to observe during daytime. So if you're an astronomer, just grab the proper equipment and try to look at the sun. It would be very interesting, especially if you have a solar maximum where you can see a lot of sunspot and other features of the solar activity.
Yes.
But in this case, I will talk a little bit about the observatory, San Miguel Observatory, its history and observations. But first, I will do a small introduction of why it's important to study the sun. I like to think I like to think of the sun like a perfect physics laboratory in which we can see extreme condition of the matter, particularly the plasma and the interaction with the magnetic fields. And these extreme conditions cannot be achieved yet in laboratories in Earth. So we have to look at the sun to see how the matter behaves in these conditions. But the problem with this laboratory is that we cannot touch anything. The parameters are set. The experiment is going independent of the observer. So what we can do is just collect the right amount of light, and we can be creative in how we explore and collect photons to see different events in the sun and try to understand and explain the intrinsic nature of the matter and the fields in these conditions. Of course, the sun is the source of stellar models, so anything we know about other stars are based on what we know from the sun. But of course, maybe the most interesting is that the sun is strictly connected with Earth. So any phenomena observed in the sun somehow will have an impact on Earth, especially in geomagnetic fields that can be measured and maybe have consequences in the technology and the people who's traveling into space. In particular, space weather forecast is a hot topic between solar physicists because, well, there are many companies that now are beginning a new space race, sending civilians to space. So in order to have assure that these missions are safe, they need a good space weather forecast in these cases. But also for astronomers, it's interesting, but it could be more interesting because, well, I cite here the quote of Robert Leighton that says, this is absolutely true, if the sun did not have a magnetic field, it would be as an interesting star as most astronomers think it is. But of course, astronomers doesn't look much to the sun because maybe it's too close, and it's interesting to see different worlds and different scenarios that are not so near us. So, but looking at the magnetic fields, you can find a lot of structures and interesting phenomena that, I mean, these are the most energetic and interesting events of the solar system. So if it's not for the magnetic fields, the sun will be absolutely boring. I'm sure about that. So what we know about the sun, we have observation for 400 years of a sunspot number, this small or big black regions appears in the sun surface. So this consists of one of the longest databases with consistent methodology in astronomy. I mean, we have 400 years observations of the sunspot number, of the daily sunspot number. So this shows a lot of interesting things, that there is a sunspot activity cycle. So the sun is more active in some stages of their evolution, and these maximums and minimums of activity also change during times, and you can have extended minimums and extended maximums, and, well, a lot of interesting features. That, of course, these are a consequence of the complex of the magnetic fields of the sun, as Leighton said. But everything changed in the 1859 when Carrington observed this massive superflare. Carrington and Hodgson. Hodgson was aficionado astronomer. So he observed a flare in white light. I mean, only observing at sunspot group, and this massive explosion in the sun. Then 2 days later, the largest geomagnetic storm was recorded on Earth. So at this time, everything changed. I mean, the sun is producing explosions, and these explosions are affecting directly the Earth. It was so large, the geomagnetic storm in that year, that affected the telegraph lines. And nowadays, a superflare of these scales will have extreme severe effects on the technology we have nowadays. I mean, it will produce massive cutoff of electric currents and, well, geomagnetic effects that can produce severe damage to communications and other problems in satellites. And also a very beautiful auroras, probably. But at this point, well, just after the Carrington event, there were a creation of institutes oriented to the observations and the link and the connection between this phenomena on the sun and the phenomena observed on Earth, especially the geomagnetic storms. So there were a lot of efforts, international efforts, put into new research and solar physics. In Argentina, in particular, in San Miguel, in this place here in the map, we had the first Latin America Solar Physics Institute created with this aim, just to observe the sun and see how sun events can affect the global terrestrial meteorologic conditions and ionospheric conditions and magnetic conditions. So in the 1930s, this observatory was born with this aim. But we can separate the history of the observatory at San Miguel into two periods. The first period we call more focus on terrestrial observations, that mostly they register and detect and catalog all the phenomena observed in the ionospheric abundances and electric currents induced in the field, in the ground, the measurements of geological data, and the sun observations was limited only to the irradiance and the amount of radiation we receive daily by the sun, and see if these fluctuations and the irradiance could affect the meteorological conditions and the fluctuations we observe on temperature and density in the atmosphere. But in the second period, by the hand of this director, this was a priest, Juan Antonio Bussolini, a more solid formation of solar telescope were introduced into the observatory. And he was very, very intelligent, and he understood that the solar observations had to be multi-wavelength. Also, that means that you have to observe the sun in multiple wavelengths due to the complexity of the solar events and the range of the temperatures. So you have a lot of things that you may lose if you observe only in one wavelength or in white light only. So in this period, with the new instruments, there were a lot of new researchers that were included in the observatory, and a lot of new projects like sunspot catalogs, detection of energetic events, capture of chromospheric and coronal structures, and radial burst events. I will talk a little bit in the next slides. So the sunspot observations are basically white light images that are recorded daily. And we must think that at that time there weren't any satellite observations. So any continuous observation of the sun had to be made with telescope network, global telescope network. And Argentina and the Observatory of San Miguel was one of these nodes of these networks. Especially, it was there to fill the gap between some Europe observatories, like Medon Observatory, and the Mount Palomar in Caltech Institute. There were like 1 hour gap between sunset and sunrise between these two places. So the San Miguel Observatory was especially interesting because at that time it was the main observation of the sun. So this is quite interesting because the photographic plates and the films used to gather these images were expensive for the observatory budget. So they were keeping most of their resources only for that hour during the daytime. So most of the images taken in the observatory were used to fill the gap between Europe and the US. But as I said before, multi-wavelength observations are necessary. So there was also an H-alpha filter to gather information of the chromospheric structures in the sun. Especially prominence and filaments are key structures to understand the morphology of the magnetic fields on the sun and how these magnetic fields can be instabilized to get out of the sun and maybe produce some geomagnetic storms and some other effects in the Earth environment. So this is an image taken with this filter, and you can see some sunspots and dark filaments correspond to the large arcades of magnetic field structures. So at this point, this instrument were used as a patrol mode to detect solar flares and transient energetic events in the sun. And here's an example of this. This is a series of pictures taken at that time in '69, where they recorded a large solar flare near the limb, taken with H-alpha. So you can see better how the structures change and how there is a large widening of these structures. So one of the main detections of solar flares are done in this wavelength, because these are very clear. White light observations, sometimes these kind of explosions of flares are so they are not easily seen by the eye. I mean, so in H-alpha, this contrast is much larger. And as I said before, the resources were limited, so there weren't many photographic plates and films to make a lot of images. So they had to carefully select the active regions that they were to observe and were to record. And I mean, this is the essence of the space weather forecast nowadays, just to try to see a sunspot group and try to see if this sunspot group is a good candidate to have solar energetic events. So in some way, the Observatory San Miguel devoted a lot of time to space weather in this case, just to study how this sunspot can produce large energetic events. The observatory also had radiometry. I mean, they had two antennas. Now only one survived. There is the 5-meter parabolic antenna. This is used to detect accelerated particles in the sun atmosphere. So it's also in context of flares and energetic events occurring in the atmosphere. So this is an example of the radiometry made by one of the antennas for the same solar flare I showed before in the '69. Maybe for other talk, I can talk about why this is so important, but I will just limit to the history of solar observations in San Miguel. But there is also a nice, interesting building that contains a celostat in the top of the building. And in the bottom of the building, this building is beautiful. It's strictly made to observe the sun. I mean, it's you get the instrument, then you build the building around it. So this is nice. So this celostat collect the sun's light, and then you can conduct the light through the building and use different instruments. In particular, there is a spectrolograph at the bottom of the building that allow to have a spectral line images, especially the calcium-2 images that are quite interesting for determining the magnetic field structures of the sunspot. And just to have a small summary, scientific work in San Miguel was quite interesting at that time. I mean, the second period was explosion of publications and researchers working in collaborations with many other researchers in the US, in Europe, and in Latin America. And this the scientific product made in San Miguel contributed to the sunspot catalog in the World Data Collection. That is one of the biggest data catalog of sunspot groups. So it also formed part of this international network for observe the sun in a continuous way, to have large observations of solar events and sunspot evolution and solar dynamics. And of course, it was a nice place to have scientific work and outreach work, where many institutions organized congress and international collaborations and, well, meetings and that, and third parties at the end of their life. And for our future prospects, Cesar told us that we are trying to recover most of the observatory. Nowadays, there isn't any work down there. It's closed, and the instruments are still inside. So we are trying to recover the infrastructure. I mean, the buildings and the instrument of the observatory, just to use this mainly for outreach, to gather the local community and schools and give some lectures and teach more about the sun and how we observe them. But also for general astronomy, it's a very nice place to have this kind of star parties and gatherings and, well, any kind of meeting oriented to astronomy. And of course, we are also evaluating to have a science there, and there is some science capabilities that can be done also with white light observations and H-alpha observations. And I think that's everything I have to say now. So
Okay.
thank you very much.
Excellent, excellent. We have a question here from Santiago Malise, I think is how it's pronounced. He says, would collaboration be probable to be able to start up this magnificent observatory of San Miguel?
Of course, we are open to collaborations, but right now we are trying to get a formal resolution from the local government, just to start working in the observatory. We are trying to recover some buildings and start moving people into the observatory, just to push our government to take a resolution about it. So after everything, if everything works fine, of course we will be very pleased and open for collaborations for other institutes and other observatories around the world.
That's great. That's great. You mentioned at the beginning of your presentation about the activity on the sun and how it directly impacts the Earth, in this Earth-Sun connection. And you also mentioned that we have about 400 years of data. Has there been any kind of study to take meteorology from the last 400 years and match it to sunspot activity or solar activity on the sun? Is there any kind of correlation at all?
Yeah. There are a lot of correlations. In particular, there is an interesting correlation about the Maunder minimum. That is a 50 years period where sunspots were practically gone. There were few sunspots. And most interesting about this minimum, that it corresponds to a little, a little winter age. I mean, ice age. That
the little ice age, right?
The little ice age in Europe. I mean,
Mm-hmm.
I think there are a lot of pictures and about this, about people doing how do you say, is walking over the Sina, the Sina River in
Right.
Paris, and it was frozen at the
It was
time.
frozen solid. Yeah.
Yeah, it was frozen solid. So yeah, there are correlations with the meteorologic data. And also there are more information about the sunspot cycles, because you can analyze different proxies to correlate with the number of sunspots. That is, you can gather geological data from glaciers,
Mhm.
and also how the ring of old trees grown, the period they grow greater when there is more ultraviolet exposure. So this occurs mostly in solar maximum. And there is also another proxies that we can estimate how the cycle evolved thousands of years ago. There is
Wow.
another extrapolations that can be done. Yeah.
Okay. And is there any kind of prediction of if you take this solar activity
Yeah.
model
Well, that
and
will be
project
the
it out into the
that
future?
will be the Nobel Prize. I mean, for more than 100 years, solar physicists were trying to predict solar cycles.
I see.
There were no luck so far. So, of course, there are a lot of models. They are trying different, like using AI models and more complex models, but still, we don't have a good approximation of the, or I mean, we can predict maybe with semi-accurate the next cycle, but the other one will be a disaster.
I see. I see.
Mhm.
Very interesting.
Yeah.
Well, I really thank you for being on our Global Star Party. I think this, you told me earlier in the program that this is your first time to do a global outreach program. So we're really happy you did it with us. So thank you very much. It was wonderful.
Thank you, Scott. Yeah, thank you
You.
very much for
Yeah.
this opportunity.
Yeah. Harold Locke makes a comment. He says, I'm excited for your community to be restoring and making San Miguel Observatory evoke a living reality. So that's wonderful.
Great.
Okay.
Thank you.
So we have one more speaker before we take our 10-minute break. And that would be Professor Karim Jaffer from the Royal Astronomical Society of Montreal, the Montreal Center. They recently conducted the 45-degree star party with the New Zealand, the Royal Astronomical Society of New Zealand, and I always mess this up. Is it the Dunedin?
Almost Dunedin.
Okay, Dunedin Astronomical Society. So it was really wonderful. They showed off their observatory. They talked about their long history, their being involved in astronomy and all the outreach work that they do. So I thought it was this beautiful, perfect kind of meeting to have online, where we were able to connect two great organizations. With was it 9,000 kilometers, 9,000 plus kilometers of distance, daytime and nighttime, and it was just wonderful. So I really appreciate you bringing that to our program.
It was such a great star party. We had a blast, and the Dunedin group, they're so dynamic and full of youth and full of energy, and their science focus was just great to see.
Yes. Yeah, I agree. Okay, well, I'm going to turn it over to you. If you have not seen Karim give a presentation, you're in for a real treat. He teaches astronomy. He is involved very much in the outreach activities of the RASC Montreal Center, and they are going well beyond their boundaries, their traditional boundaries, and they're reaching people from around the world with their programming, not only on Global Star Party, but stuff that they're doing completely on their own. And they have the right attitude of inclusiveness and the passion and inspiration that they're bringing to the audience up in Canada. They're spreading it everywhere. And so really happy to have you back on so soon after doing a star party just on last Saturday.
Oh, thanks so much, Scott. It's a pleasure to be back, and hi to the audience for the GSP. It was nice to see you on Saturday night, and it's nice to be back on a Tuesday night. It's been a tough start to the term to try to balance things. So I've missed a few Tuesdays, but I'm really glad to be back with everyone. And Scott, I don't know if you've noticed when you've seen the posters that Scott puts together and the topics and the videos that he chooses, but he puts a lot of thought into kind of connecting these great ideas into a theme that really can energize you. And even if the talks aren't all directly related to the theme, there's kind of an underlying current of outreach and of discussion, and it really sets the stage. And so when he wrote the email today or last night, basically suggesting Lookback Time, I thought, all right, great. I'm going to talk about the expansion of the universe. I'm going to talk about the galaxies. I'm going to talk about how large the universe is. And then I stopped and I remembered a discussion that I had on Saturday, early Sunday morning with a couple of students who were messaging me after the 45-degree star party. And then in class today, another discussion arose after class with a few of my students. And I thought, you know what? Let's talk look back time, but let's talk about it in a different way. Let's talk about the look back time that happens with what we do in our solar system and the astronomy we do when we go out at night and look at solar system objects. So I want to talk to you a little bit about that tonight. But before I do, I want to just do a brief check-in on a couple of the things that I've mentioned to the GSP audience in the past. One thing I will mention is those of you who know of some of the universities up here in the Montreal area, McGill does some amazing work, especially the McGill Space Institute. And they've got an awesome James Webb seminar coming up later next week. But Space Concordia is a group of students that put together amazing work, rocketry, satellite programming divisions, you name it. And they have started a podcast series during COVID. And myself and Virginia Pacheco, one of my former students, are their next podcast coming up later this week. So if you take a look at Space Concordia podcast, you'll get to hear a little bit more about outreach in Montreal and in Canada. So a few months ago, I started talking to you about this world record attempt that was going to happen in mid-September, and it has happened. It's concluded, and Mark Thompson lectured about astronomy for 140 hours.
Holy smokes.
He got short naps every few hours. He managed to follow the NASA regimen of 26-minute cat naps like every 12 hours to just rejuvenate himself. He had liquid meals, not that type of liquid meals. I'm talking Ensure and those types of liquid meals. He had his temperature being monitored. He had his electrocardiograms being monitored, saliva tests, blood tests. He had hallucinations. He definitely went a little bit sideways a few times, but he made it through the 140 hours. And what's really incredible about this is the whole time he was being monitored by groups researching sleep deprivation. And so his focus was the research on sleep deprivation, as well as raising money for a children's charity called Bernardo's in the UK. So if you're interested in learning more, visit his website. There's still a possibility to give funds to Bernardo's. He did exceed his goal of £10,000. I believe they're almost at £13,000 now. And it's just amazing what he's done. And we're waiting to hear back from Guinness. They're reviewing all the video and making sure that he actually didn't stop talking for more than, I think it's 45 or 30 seconds at a time, and that he was able to follow through the entire time following the rules. But we had him on as a guest on Monday on Astro Radio, the group that I'm on with Reach Out and Touch Space. And he talked all about this effort and all the people involved. So I highly encourage you to visit and listen to Reach Out and Touch Space, get to know a little bit of the panel. They do amazing work there in the UK. Here in Montreal, we have our next event coming up for International Observe the Moon Night, and you'll recognize our speaker because he was here just a little while ago. It's Chuck Allen, the VP of the Astronomical League and one of our RASC Montreal members. And he's going to share the solar system moons, because for Observe the Moon Night, why limit yourself to one moon? Let's just go whole hog and go for all the moons in the solar system and learn a little bit about all of them. So I invite you to join us for the Solar System Moons talk. But what we're going to talk about tonight is very much based on this idea of look back time. Now, look back time is this idea of when you're looking at the light from an object, how long ago did that light leave the object to come to us? So what exactly is the picture we're looking at? And on Saturday night, I shared a couple of the images that I share with my students live using the EV scope when we look at the Big Dipper. And when we look at the Big Dipper in the Northern Hemisphere, we really get to enjoy some galaxies, some nebulae. And so the galaxies that we look at, there's M81 and there's M82, which we love. And they're about 12 million light years away. And you talk about that with people and you say 12 million light years away, and they can't connect with it. 12 million years is not a number that they can connect with. But they love to look at the galaxies, and it tells them that these objects are really, really far away. And you can discuss a little bit about the expansion of the universe and galaxies even further away and Hubble deep space. You can share the Whirlpool galaxy, which is 23 million light years away, and you can actually see a Seyfert active galaxy having its dust being drawn out by this large spiral galaxy. And it's incredible to see, but it's hard to connect with. And so then I share with them the Owl Nebula. And the Owl Nebula is a planetary nebula that's about 2,000 light years away. It's about 9.9 light years across. So it's expanded a fair amount since it was born. And we believe that the Owl Nebula was formed about 8,000 years ago. So then you start to actually connect. And Book Davies made an awesome comment tonight about trying to relate this to actual numbers and actual moments in history that people can relate to. So the Owl Nebula, the light takes 2,000 years to get to us, which means that what we're seeing is how the Owl Nebula was at the birth of the Common Era. Basically, the birth of Jesus Christ for those that follow the Judeo-Christian calendar or the Judeo-Christian way of recognizing history. But that nebula was formed 8,000 years ago, which means it was formed right around 6,000 BCE. And at that time here on Earth, we were just developing the civilizations of Mesopotamia. We had the very first thing you could actually call a city formed here on Earth. And when that light of the planetary nebula being formed got to Earth, it would have taken 2,000 years. So that's in 4,000 BCE, when the Mesopotamians would have invented writing, and the Egyptians had just started developing their deep culture and started building some of their amazing archaeoastronomical objects like the pyramids. So when we look at some of these objects, we're talking time frames that are incredibly large, and we're talking distances that are incredibly far away. But that's not even a smidgen of the size of the universe. And so you tend to lose the general public and introductory students very quickly if you start there. And so what I like starting with instead is actually looking a little bit more at scales you can recognize. So you look at the moon. The moon is 385,000 kilometers away, roughly. So it takes just under 1.3 seconds for light to get to the moon and come back, because light travels at about 300,000 kilometers per second, or 186,000 miles per second. We have amazing lunar reflectors that were placed on the moon by the Apollo mission, where you can actually see this experiment having been done. And they made fun of it a little bit in the Big Bang Theory. And, they set up on a rooftop and they sent the signal. But this experiment has been done and is still done often in a lot of universities using remote laser guidance that can actually hit those reflectors dead on. And you use the speed of light to confirm some of the details of the moon. But that's the closest man-made object on an astronomical body in our solar system. When we look at the actual exploration of the solar system, we have gone much, much further than that. And the reason why this took context for me today is because I've been talking to my students about the planets of the solar system. And we started talking a little bit about some of the things that we use to explore these planets, not just the probes, but also the rovers. And today, Dr. Farah Ali Bey from JPL, who we had on at RASC Montreal Center for a Zoom talk last December, she posted that today they just sent a packet of activities for Perseverance, because over the next few weeks, Perseverance is in conjunction with the sun. So they're unable to actually send radio signals and commands back and forth to Perseverance. So they get a little bit of a hiatus and they wait, hoping that everything goes well and Perseverance doesn't fall into a ditch or something, right? So you have all of these constraints when we're exploring the solar system in communicating with the objects that we send out. One of the things that I love telling my students is, we have this deep space network that allows us to communicate with all the probes and all the satellites. But you look at something like Curiosity on Mars. Curiosity has an 8-minute window every day to communicate with the Mars Reconnaissance Orbiter. And it can send up to 100 to 250 megabytes of data in that 8 minutes. It takes 20 hours for the Mars Reconnaissance Orbiter to send that information to us here on Earth, not because of the distance, but because of how slowly that data can actually be sent in a reliable fashion. So when we're talking about distances and times in the solar system, there's a whole bunch of factors to bring into play when we're talking about man-made devices. And we can go beyond that, because the 2 Voyager probes have left the heliopause. They're away from the influence of our sun, but we can still communicate with them. It takes 21 light hours to send information for us to Voyager 1 or to Voyager 2, and they have a little 20-watt signal that they're capable of sending back and forth to us. That's about the amount that you use in your refrigerator light bulb when you open it at night to get a snack. And we're using that to explore interstellar space. Wow. So this whole concept of time in our solar system really takes on another meaning when you start thinking about the way in which we respond or communicate with the objects that we ourselves build. But let's face it, we're astronomers. So when we want to talk about objects, we want to talk about what we can see. And if we start looking at the planets and the moons of the planets, we're looking most of the time at sunlight being reflected off of those planets. So you look at sunlight getting to Mercury, it takes 3.2 minutes. But then that sunlight has to bounce off Mercury and get to Earth for us to see that tiny, tiny little dot just above the horizon if we're lucky and it's the right time of the year. Venus, 6 minutes, and then again, it has to bounce back to us. So the light actually travels a total of just over 10 minutes to go from the sun, bounce off Venus, and get to Earth if Venus is at maximum elongation, which is when we typically try to look at it because we get the best picture because it's actually at a really nice vantage for us. A right angle, we see a very nice phase of Venus. But for the planets beyond Earth, when we look at those and we want the most detail, we look at those when they're in opposition, when we are lined up between the sun and those planets. And in those cases, the light gets to Jupiter for 43 minutes, bounces off Jupiter and gets to us. It takes an extra 35 minutes to come back to us. And so you might say, all right, well, I'm looking at light that initiated from the sun around 78 minutes ago when I'm looking at Jupiter. But I'm seeing Jupiter 35 minutes in the past. And that's what you're doing. You're seeing Jupiter 35 minutes in the past. And that sounds all well and good until you realize that Jupiter and Saturn are 2 planets that actually give off a little bit more energy than they get from the sun. Jupiter more, Saturn a little bit less. And the extra energy that they give off, the extra radiation, is left over from the formation of those planets. So a little bit of the light that you're seeing actually originated when those planets were first formed around 4 to 4.5 billion years ago. Now that sounds really interesting, but you're still seeing the surface of the planet 35 minutes ago, Saturn 71 minutes ago, and et cetera, moving out to Uranus and Neptune if your telescope's good enough for you to actually be able to see Neptune. So that's the time that we are seeing, the look-back time when we look at the surface of those planets. But it's actually even a touch more complicated than that. Because when we're looking at the light from the sun, we saw that the sunlight takes 8.3 minutes to get to us. And we saw that the speed of light is 300,000 kilometers per second. Now, the sun is about 700,000 kilometers in radius. So you would assume that when the energy is formed at the center of the sun, it'd take just about 2.5 seconds for it to come out from the sun, right? And the answer is wrong. It actually takes almost 100,000 years for the energy formed in the core of the sun to make its way out to us. And that's because when that energy is formed, the really, really high energy gamma rays at the center of the sun, when hydrogen fuses into helium, which we talked about back when we talked about the life of stars earlier in the summer, that light can't make it out because the area in the core is really, really dense. You have 150 times the density of water at the core of the sun, which means as soon as that gamma ray comes out from that first fusion reaction of hydrogen fusing to helium, it gets absorbed by something else, re-emitted, absorbed by something else, re-emitted, absorbed by something else. And when it's re-emitted, it can be re-emitted in any direction. Now, physicists, we call that the random walk. And the random walk is basically if you picture a drunk person standing at a light post, trying to get to the next light post, their every step is completely chaotic. They're moving in any given direction. And so it turns out that if the next lamppost is 10 steps away, on average, it takes them 100 steps to get there. Now, that's only in 2 dimensions. The sun is 3-dimensional. So now you've got this extra dimension of chaos, of this random disorder of walking. But those walks, those steps, are actually absorptions and re-emissions, absorptions and re-emissions. Uh-huh. So if you picture the sun as having these absorptions and re-emissions happening at every 10th of a millimeter, to get out from the core of the sun to the next layer could take up to 1 trillion steps before you can get out that far. And that's why the actual timing that it takes just to get out from the core is almost 100,000 years. And then at that point, it gets to this awesome convective layer. And the convective layer is like a little lava lamp, and it just brings the light up, and it brings the light up, and it cools it down. And we can actually see the granules on the surface of the sun from these little lava lamp granules that form in the convection layer. And what's really interesting is that the convection layer has 2 parts. It has a superconvection layer, where those big, big cells taking tons and tons of plasma, they can last for days. But at the very top, there's these microgranules, and those microgranules only last for a few minutes. And when you compare your observation for the types of images that people like Gary Palmer can get out of their pictures of the sun to the simulation that we get on computer models, you have incredible matching. And so if you could peek through the surface of the sun all the way down, you would see these incredible, incredible granules all over the sun, carrying that energy that's lasted for 100,000 years coming out from the core of the sun and bringing it really, really close to the surface. And then it makes its way to the very top of the surface. And 8 minutes later, we get to see it here on Earth. So when we're looking at sunlight and we're sitting there and enjoying a really nice warm afternoon in the fall, looking at the leaves changing colors, believe it or not, the light that's helping us do that is 100,000 years old. And that's what's helping keep us sustained here on Earth. And with that, I want to do a nice outro that Scott made for us here in the Rask Montreal Center. And so we now can have this in all of our awesome videos. Thank you, Scott. And thanks, everyone. I hope you enjoyed.
You're very welcome, Karim. Thank you. That was fantastic. I loved it. You know, I always learn something from you, Karim, and you know, not only new information, but presentation style and all the rest of it. I think it's fantastic. And I'm really glad that you were able to make it for this Tuesday Global Star Party.
Well, guys, thanks very much, Scott.
Thank you, Karim. We're going to take a 10-minute break, and I'm going to leave my microphone on because I have a habit of turning it off and then forgetting to turn it back on. So, but we're going to take 10 minutes, and that's enough time for you to grab a sandwich or a cup of coffee or stretch your legs. So we'll be right back. We have more presentations to give you, and so stay tuned.
¿Qué onda?
¿Qué haces, Max?
¿Cómo va?
Tenemos invasión argentina hoy.
Sí, estamos a pleno. El sur dijo presente.
¿Qué estará haciendo César? ¿Pizza o pasta hoy?
Capa de ravioli. No, yo me hice una tarta. Está muy buena. Jamón y queso y huevo.
Hey there, welcome to NASA Launchpad. I'm your host, Justin Tully. So, what's the furthest you've ever been away from home? For some of you, that might just be a couple miles from your house. Or you might have gone from one coast to the other, or maybe you've even gone overseas. But hey, none of you have gone nearly as far as some of NASA's missions. I mean, let's just look at any of the Apollo missions. One way from the Earth to the Moon is about 385,000 kilometers, which is roughly 239,000 miles. 239,000 miles? I'll be lucky if my car can make it to 200,000. Well, even the moon isn't too far away in the grand scheme of things. I mean, NASA has sent missions to Mars, Jupiter, and Saturn. They've even sent spacecraft past Uranus and Neptune and all the way out of our solar system. I'm referring, of course, to the Voyager mission. Never heard of the Voyager mission? Well, you probably weren't born yet when it was launched. The twin spacecraft, Voyager 1 and 2, were launched in 1977 to study Jupiter and Saturn, but were able to continue their mission well beyond that. They're both still going strong today, but way, way, way far away from us. Voyager 2 is now more than 85 astronomical units away from Earth, and Voyager 1 is more than 105 astronomical units away. Okay, wait, what's an astronomical unit? Well, basically, it's a unit of measurement that helps us put things in perspective. You all probably know how far away the sun is from Earth, right? About 150 million kilometers, or about 93 million miles. Well, an AU is based on that measurement. 1 AU is the distance from Earth to the sun. So rather than getting into all those zeros, you can keep it manageable using AU. Like instead of saying that Voyager 1 is about 15.7 billion kilometers away from the Earth, we can say it's about 105 AUs. Still not sure? Okay, let's look at it like this. If you're going to give someone directions from your school to your house, you wouldn't tell them to go about 400,000 centimeters and then take a right on Elm, would you? And going the other way, if you were measuring, say, your windows for new curtains, you wouldn't say they're 5/10,000th of a kilometer wide, would you? Of course not, that'd be ridiculous. You use the unit of measurement that makes the most sense and allows others to quickly understand the proportions. To measure huge distances in space, astronomical units just make sense. All right then, moving on. And speaking of moving, there's another NASA spacecraft that's making its way to a very distant destination. It's called New Horizons. Now, it's actually already been launched. In fact, it was launched on January 19th, 2006, but it's not even close to its major points of interest, Pluto and the Kuiper Belt. There's still a long road ahead of New Horizons. How long? Well, we caught up with Alan Lunsford, NASA technologist on the New Horizons mission. And he gave us a little insight into the timeline of the project.
It takes a long time to get to Pluto. It's 35 times further from the sun than the Earth is, 35 AU. To put it in context, Jupiter is 5.5 AU away. So it's a lot further than Pluto. In fact, we launched, and within a year and a half, we'd flown past Jupiter. And it's still going to take 8 more years to get to Pluto. It was the fastest spacecraft ever launched, remember? And it's still going to take that many years to get to Pluto. And we don't have the fuel to slow down, so we just fly past, and as we're flying past, we take all the pictures we can, store them on board, and then take the time after we've left Pluto to broadcast them, transmit them back to Earth, and do our analysis.
See there? Scientists really do talk about AUs, astronomical units. That makes sense now, right? Anyway, something else he mentioned was how New Horizons has already passed Jupiter. And how it did so is actually really interesting. They used a little something called gravity assist. This technique has also been referred to as the slingshot effect. And it's been used before on several missions, including Voyager. It helps save fuel and is a big part of the reason why these missions are able to succeed. Basically, the spacecraft takes advantage of the gravitational pull of a body to slightly alter its trajectory and gain speed. So the spacecraft is being pulled by the gravity of the body, but it's moving quickly enough that it doesn't enter orbit. The force of the gravity is added to the spacecraft's velocity, increasing it. The planetary body is also affected, but because its mass is so large, relative to the spacecraft, its change in speed is minuscule. As you can see in this animation, as New Horizons passes Jupiter, its trajectory changes and its speed increases as it slingshots past. Now, both of those factors are important because, as you can see, they help put New Horizons on the right course and timeline to pass very closely by Pluto. See, this isn't happening by chance, and it's not easy. All of this has been planned. Researchers had to map out all of this in advance, doing all sorts of calculations about where planets would be when, the necessary velocity for the spacecraft to arrive at the right time, the distance New Horizons had to be from Jupiter to maximize its increase in velocity. It really boggles the mind. And I thought figuring out the logistics of an overnight trip to Grandma's was complicated. Well, that's it for now. Until next time, I'm Justin Tully. Thanks for watching NASA Launchpad.
Hi friends, Vivian White here from the NASA Night Sky Network, and I just want to invite you all to join us for the Global Moon Party happening October 9th from 3 p.m. on, that's Pacific time, 6 p.m. Eastern time. We are going to have such a blast. We have great folks from the International Observe the Moon Night joining us. We have NASA friends from the Visualization Studio and moon treks and all over the place. We have Icelandic poets to talk about the moon, presenting new work that they're doing. Space agencies from around the world will join us, and we hope you will too. Please get the word out. Let everyone you know who loves the moon know that we are kicking off the International Observe the Moon Night this October 9th. See you there.
Well, thanks for hanging in there with us. We're back, and we have coming up next would be Molly Wakeling. Molly is a great astrophotographer, great image processor, a great scientist, and she is someone that has been on many global star parties with us, and we're really happy to have her. Molly, are you with us now? I don't see her yet. Okay, so we might have to wait for a little bit, but I'm sure she'll be on a little bit later. Okay, well then we will move on to Nico, Nicolas Arias, also known as Nico the Hammer. Nico is down in Argentina, and Nico, thanks for coming on to our program.
Hi Cesar, hi everyone. How are you this night? Okay, tonight's topic is about the look-back time. So I prepared a little presentation about that. Let me share my screen. Okay, can you see it?
Yes.
Okay. Well, look-back time is something that we used to talk a few times in the after parties. That we would like to think about that we are looking literally the time. And well, as Karim was talking about the sun and the time that the sunlight or the photons of the sun reach the earth, and that was the 8 light minutes And well, you realize when you are observing that you can see similar dots or stars in the view, but not all it happen at the same time. Okay. We have here two examples, and the left one is Proxima Centauri, that is the near star to us for the sun, and the light of Proxima Centauri takes a journey of almost 4 years ago. So everything we look about this point has happened 4 years ago. So you need to wait 4 years to see if something happened today. These things is so amazing to be observing and thinking, and you keep looking at the sky at night and see how large the universe is. And I start thinking, okay, how far can I observe with my telescope from my backyard? And I found some information about quasars, and this particular quasar 3C273 that is located in Virgo constellation. A quasar is a black hole in the center of a galaxy that it starts to absorb the matter so quickly, and the rotation velocity and the accretion disk, he produced a giant amount of energy, and it's become the most bright object in the universe. It's a black hole, but that amount of energy makes it that bright. And this quasar is particularly the first quasar discovered. And
Looks like we may have some Nico, if you can hear us, your broadcast is a little frozen. We'll give you a few minutes here, a couple of minutes, see if we can bring it back. Otherwise, maybe we'll have you relog in. Now, Nico uses a Dobsonian telescope, and he's pointing out some objects like 3C273 and some other objects. I remember finding 3C273 through a 13-inch Dobsonian that I had at one time, and I remembered that it appeared as like this faint blue star. And I remember having a conversation with an astronomer at Palomar Observatory that was working on the 200-inch. And I was really surprised when they told me that, that the quasars are so far away that they look like, they look star-like even through the biggest telescopes. So, you're back, Nico. Great.
Yeah, my internet connection just dropped.
It happens.
Yeah. Okay.
It happens.
I was talking about this quasar. Can you see the screen?
Not yet. You're not sharing yet.
Okay.
You were talking about how far you could see with your telescope.
Okay.
That's when it froze.
Let's go there again. So I found information about this quasar in the Virgo constellation. That is the first quasar discovered, and one of the farthest objects that we can observe. A quasar is a black hole that absorbs matter such velocity that the accretion disk produces this amount of energy and exposes and makes the quasars be one of the brightest objects on the universe. And this particular quasar is located at 2443 million years ago. It's really, really far, and it's one of the farthest objects that we can observe. So I did a little research about what was happening here on Earth at that time. And well, it was at first snowball Earth, about 21 or 2400 million years ago, and was the great oxidation event when cyanobacteria start combining the CO2 with water and sunlight energy, and the waste reaction was oxygen. So it was amazing to find out what was happening here. This is a simulation of how Earth would like on that time. So well, I start for a few nights trying to find the quasar, and we are looking real back in time, and this is a sketch that I made that night, and that little dot is the quasar. I could find it. I was like half an hour looking and checking on different softwares to see if that was real. The quasar was a really nice observation, and most significant about this, about the time, about the far I was looking at. And this on the right is a picture I take with my dog and the Quid 5, to check that. And yes, this was the quasar. So well, I like to share this short presentation to talk about this, about the Lookback Time, and how wonderful it's observing that, because you usually see the stars and dots, but when you start to think about the time, it becomes an amazing observation. So thanks,
Wonderful.
Scott.
Thank you
Thanks
so
to
much.
everyone.
Thank you. Nico, I was, while you were offline there for a couple of minutes, I was talking about my own observation of Quasar 3C273. And it is amazing. The feeling of that you're looking so far back into time, and then you match that with, you think about how much further into space it has traveled, because the universe is expanding. So it's also been expanding all this time, and yet we're seeing it at kind of a frozen point in time that we can see, and it has traveled all that time to get to you. And what's even more remarkable is that when you're looking through a telescope, you see these things live. It's not a reflection. It's not a recording. It is, these are real photons really hitting your retina. So there's some special feeling about that. I think that you have that.
As you say, it's a fixed portion of time, because we don't know now or tomorrow what happened there. The dot is not there, probably.
Right, exactly. Right. Okay. Wonderful. I'm glad that you made that presentation, Nico. Thank you very much. Yep. Somebody made the comment that to bring the hammer down. So you are Nico the hammer to us. Thank you, Nico. Okay, so up next is Gary Palmer, who's been waiting patiently in the UK. What time is it over there, Gary?
It is 3:30.
3:30. Okay, you got the stage for as long as you like. Okay, it's
very late.
That's all right. We get used to it. Yeah. So anyway, nice to be on here. Nice to listen to everybody this evening. Been some very interesting talks.
Yes.
Yeah, I haven't really decided what to talk about, and somebody asked me to do some bits on processing on the moon, which we're doing in a minute. But I did think, sort of looking back on things, and looking back in time to actually looking back on images that I've taken. Certainly on solar, because it actually marks a decade this year that I've been imaging the sun in HA.
Wow.
So it's quite surprising how bad your images are when you first start out and where you get a decade later. So just to prove that I did take bad images sometimes, that was one of the first HA images that I did 10 years ago. So it sort of moved on, and it didn't take me long to work out what was going on and where I was going wrong. So within a couple of years, it sort of moved on to this, and that was with the Coronado 90. So to try and do that in 2012 was very hard. It wasn't easy in that day and age, basically on cameras and the limitations of the equipment and probably knowledge as well. The one thing that I learned very, very quickly in solar is don't listen to everybody, follow your own path. Yeah, if you listen to everybody, then you're probably going to struggle quite a lot. So, and then sort of moving on to this, you know, moving on to these sorts of things. I mean, that's a few years ago now. Solar flare exit points on the surface. You know, you're doing this sort of stuff, and now it seems that you're running out of things to do, but you aren't. It's the lack of activity on the sun. Same thing again, the sort of solar flares in this day and age. So that was really sort of where I wanted to go on that, and sort of say that, you know, things change, equipment changes, and probably in this day and age, it's a really, really good thing to be getting into astronomy because of those changes in the equipment. It's fantastic what you see people doing from around the world now. So moving on to the processing, I put up a lunar shot earlier, and somebody said, can you sort of run through this, how you're bringing out the colors in the images? So I thought, well, the image was taken last night, so it was a video run up and captured in here. I can't open the roof up, it's still raining. I was on the moon for a couple of minutes earlier, but the rain soon started to come back in. So I was actually going to sort of run this up in how we capture it. But at the end of the day, it's done on a deep sky camera. It's not necessarily a planetary camera, but most of these CMOS cameras, you can switch into planetary mode now. So by switching it in and coming down on the image size, the resolution, cropping it off, because if you start recording videos on these large cameras, they won't process. There's so much data there now coming off of the cameras. And some of the solar images that we've been doing over the last sort of 4 or 5 months, they're equating to 20 gigabyte of data in one video. So you've got to be quite careful when you're starting to do this on large cameras, how big the video file is. But this is the video file loaded in. It was on a 90mm telescope, and it used an ASI 2600 color camera. So it's all loaded in. All we need to do is wander along, look at a few of the images and try and pick out one of the sharper ones by sliding the bar at the top there. So we'll go for something like that. And then what we're going to do is analyze the image. And what I do say to people is ignore this graph. Certainly here for the last, forget how long now, been suffering with a lot of high cloud. Most nights of the week, there's a lot of high cloud moving over, and when we're getting the changes of season, you'll get that even more over this sort of next 4-week period, 5-week period. So this graph will vary a lot, and I've had this down really, really low. I've had it down at below 25%, still got nice images out. Once it's analysed it through, we need to look at the amount of frames. There's 500 frames there. These large format cameras, you really don't need a lot of frames. Some of them, sometimes less is more. So on this particular one, we've got 150 frames, and we're just going to stack that up. Yeah, first off, we need to place some alignment points on. So what we need to do there is make sure they're quite large, because the image file is large. You'll need the alignment points large. And don't be scared to raise this. Sometimes you're actually better raising this up. Certainly if you've got slow computer, you'll want to raise it up. to speed it up a little bit in its process. We apply those across the image, and then we stack. Shouldn't take too long. Okay, so we open up Registex. We're going to just sharpen the image a little fraction. That's come into there. The initial layer, I normally set the initial layer on full disk shots to 1. You have to keep an eye on this, certainly on the limb of the moon. You end up with some, if you go sharpening too much, you end up with a really bright line around the edge, and it's really distracting when you've actually got your finished image there. So it's quite good to keep this initial layer down to 1, and then just keep your slider 2 down quite low. So just going to go for somewhere around the 10 on slider 2, and then we click do all. Now, I've had a couple of things people saying to me about different artifacts and different things going on these. And this happens in solar as well. When you're processing large format images, Registex wasn't made for this. It was made, it must be sort of best part of 15 years old now. And I think this version here is probably at least 10 years old, somewhere around that. And it's not been updated since. And it can't handle sometimes the screen resolutions on modern monitors and modern computers. You do see lines go through the image. Those lines are not always in your image. They're actually just the screen rendering of the system. So it's quite a good idea to save the image and actually have a look at it in something like Photoshop before you start panicking that you've got lines and go scrapping the images. What we will do though is the terminator line down here is quite dark, just with the phase of the moon. So we're just going to brighten it a little bit on the histogram. Yeah, and if you double tap on that area somewhere here, it will refer to that area. You'll see it live on the screen. It's just going to raise it up a little bit. And that's just not going to make it too dark. If you image full moon shots and you've got reducers on, quite often you can end up with some haloing around the outside of the moon in the dark area, and it's really hard to correct. It's not an easy thing. So by lighting in it, you'll balance out the difference between the black background and the actual surface of the moon. Once that's done, we can save it. And then we're going to drop that down, open up PixInsight, and then I'll just grab the folder with it in and drop the image in there. Okay, so we've got our green moon. First thing we're going to do is crop it in a little bit because of the field of view. Yeah, we don't want all of the black around the edge, and it just make it a little bit nicer. So if we go to dynamic crop, still leave some black on it. And then what we need to do is balance out this green, yeah, to remove it. Easiest way of doing that is to use linear fit in PixInsight. It's very good at balancing out colors on planets and lunar shots. So if we separate it, so we're going to use the button up here to separate it into its separate colors. Move these over just so we can see what's going on. So you can see the difference in the colors there between the blue, green and red. You see the blue is always a lot darker. So we bring up linear fit. And then what we're going to do is select the green channel. The green channel is the one that's got the most colouring through the 2 green pixels, or doubling of green pixels. It's probably the easiest way of saying that. Apply it to the blue channel, apply it to the red channel. And then if we go into channel combination, we can recombine those channels back together again. And if you click on here, you'll see it comes up with an R on the end, G for the green, blue, and then apply. Okay, so now we've got our image. Just going to close these off so that we don't get confused as to what's going on. Okay, so it looks quite mono at the moment. If you try adding in color in Photoshop, you'll find that the way that Photoshop looks at the colors, it can really make some areas look quite bad on lunar shots. And what I've found is by adding the color in, using the saturation in PixInsight, it's a lot nicer. It's a lot more generic through the image. So if we go to curves transformation, open that up, click on the image so it's blue and highlighted. I'm just going to move that over a little fraction, and then we're going to put up the live view. So as I'm making adjustments, you'll see it on here. In the curves transformation, click on the S at the end, the saturation tool, and then where the first 4 boxes join is raise it up. And as you raise it up, you'll start to see the color coming in on the moon. Don't go too mad, because you can do this twice. So generally not as much on the second pass. That's right, still got that open. Need to close your dynamic crop, otherwise it won't apply. There we go. Okay, so then we lower it for the second one. Just raise it up a little bit. Don't want to go too mad with it. Okay, so once that's done, we can save it off and then send it into Photoshop. If I just save that to the desktop for a second. Okay. So the first thing to do is rotate it in the right direction. There we go. And then you can do a number of things in here. One of the easiest ways of sharpening this is actually to duplicate the image. So if you duplicate it, that opens in the next tab, and then turn this to a mono image. So just going to turn it to mono grayscale for a minute. And then we can just take a little bit of the noise out. So normally do a despeckle. And then if we go to sharpen, yeah, do an unsharp mask. So that's already preset in there anyway for that. And then you might just want to brighten this a little bit, just so that it's not so dark on the background there.
That's looking more and more incredible.
So what we're doing there is we're just brightening the background a little bit so it doesn't look so dark and black in the terminator line. Once you've done that and you're happy with it, you can spend a bit of time on this and play around. If you select it all, copy it, and then go back to your color image and paste it over the top. Once you've pasted it over, under your layers there, you now want to adjust this to luminosity. And then you can adjust the percentage that you want to bring in that layer. Once you're happy, then you just combine them together. Yes, to flatten the image. The last thing I would normally do on this, as it had the reducer on and we were running quite fast, you can see it's a little bit bright around the edge there. I would just blow this up. And then I would just go into the blur tool. Yeah, and just run the blur tool up just around the edge there. And it would just take off the sharp edge on it. and that's your moonshot.
Wow. It's beautiful. All the variations of color and
yeah, you
subtle
can play around with
shading
this.
and everything. It's wonderful.
Sometimes you find that you can get it a little bit light on the blue, and that can be down to the filter that's in front. Yeah, whatever filter you're using. And if you don't like that blue, you can just go into something like selective color. Yeah, select the signs and just take it back. That's it. You'll see it's died back down over here. Yeah, and then that's it. That is the easiest way of extracting the color out on the lunar shots.
Beautiful. Beautiful. That's great. Cool. Well, it's important to note that the moon played an important role in our understanding of look-back time. Even though it's such a close object to us, the moon moved perfectly in front of the sun in the eclipse of May 29th, 1919. So Einstein had predicted that if the sun was obscured by a total eclipse, that we could photograph the stars, the background stars, and then photograph the same region without the sun being in the way, and that we would see a shift of the stars as the light rays bent around our own sun. And so this was the start of trying to prove Einstein's theory of relativity, and it was successfully done during this particular eclipse. It had been attempted before, but you have to understand that emulsions, the film emulsions, were extremely slow. I don't know, something like probably like somewhere around ASA 6 or something, or ISO 6, as you might think of it. And so they needed a long duration eclipse to photograph the background stars. And that particular eclipse was over 6 minutes. So it was really spectacular. They sent down 2 teams to photograph the eclipse. This was Sir Arthur Eddington, who was working with experimentalist Frank Watson Dyson. And so they went down, and one of them went to the island of, I don't know if I'm going to pronounce this right, Principe, off the west coast of Africa. And the other team went to Brazil. The telescope that was sent to Brazil had some problems with the focusing mechanism, and had shifted during the exposure. The other telescope was perfectly fine. And so for a very long time, up until maybe about the 1950s, there was an argument over whether or not that experiment was valid. But nevertheless, after that experiment was done in 1919, Einstein won worldwide fame. And but as scientists always do, they want to be absolutely certain. And of course, the experiment of light bending around galaxies and black holes and all kinds of stuff has been done again and again. There was a recent example of from Hubble, I think it was published this month, of an Einstein ring, which was just absolutely beautiful. And so anyways, I think that your choice of image processing the moon tonight, Gary, was a very good one. So
thanks. Thank
you.
It's one of those things that you never really lose interest in imaging. I think, and if it's clear enough, you're going to try and get as close as possible, the same as any other target in the night sky. So it's something that's always there, and it's always good to hone your skills in on.
Absolutely, and it's amazing to see you take those raw files and so quickly go through the image processing process when you did it in just a few minutes, and showed us really a mind blowing. So thank you very much.
It always used to annoy me with lunar shots of, if I wanted to draw that color out, that a lot of the programs would oversaturate. So, you know, when PixInsight came along, and I spoke to a couple of people, and oh no, you can't use it for planetary work, and you can't do this, and you sort of sit down there and play around with a few of these processes in there, and you know, away you go. You could do a lot more in there if you want. It's but it's just an easy thing. But I think the thing is now is, you know, is the equipment. I mean, I've got cameras sitting here that do 500 frames a second.
Wow.
You know, if you stick those onto something like Jupiter,
very powerful equipment, you know.
Yeah, you know, these are,
it's true.
The advances, you know, and we moan about a camera with a second delay on it these days.
You know, during one of actually the very first eclipse I went to, I was invited to go to Mauna Kea with, there's a science program on public broadcasting channels called NOVA. And so I was invited to be part of the NOVA film crew, and I went to Mauna Kea, and we were imaging, filming actually on 35 millimeter motion picture film, the eclipse itself. But we were set up right in front of a telescope called the CFHT, which stands for the Canada, France, Hawaii Telescope. And it's a huge instrument. David Levy and I were just talking about it earlier in this program. But of course, they had electronic imagers on there. This is the 91 eclipse, and so the superintendent of the observatory was talking about how the young, professional astronomers complained how long it took to get an image down from the telescope, which was, you know, it was just seconds, okay, that it took. This particular guy that was superintendent remembered when astronomers were still shooting on film, which, you know, a much different scenario, you know.
This is one of the reasons why I started playing around with double stacking, because in the days of having the 90 millimeter, and you know, I'd had some of the Lunts come over, and the solar scopes from the Isle of Man. The biggest problem was that the cameras, to actually get through all of the amount of glass that was in the double stack system, it was really hard. Your exposure was right up. You were having to run, you know, the gains up on the cameras or the ISOs up on cameras. And you were finding that you were running down to, you know, probably 5-6 frames a second. Well, you just can't do it. You know, the images were so noisy. And that was the reason why I started playing around with it. It was to come up with another way of doing the same thing, but allowing 30% more light through the system. But the cameras now are totally different. You could image on some of those older pieces of equipment that we had quite easily. But in that day and age, you couldn't. You know, and it makes a massive amount of difference. If you're after something fast moving on the sun, it wasn't happening. And I can remember when I posted up one of the first images from one of the double stacks that I'd made, and somebody goes, well, you can't do that. It's like, well, you can. It's here in front of you. But the conception was that you couldn't do that. You know, it wasn't possible to do those things. So, you know, still playing around with it now. And now the sun's getting active again. It's showing up a lot more detail and a lot newer things. And there'll be a lot more things we'll play around with probably next year now. As we're coming out the sort of the sun season here, sun's going to be low for the next sort of 3 months, 4 months. You're not going to get much work done on it, but it is interesting looking at some of the stuff, even, you know, newer people coming into the hobby, how quick they've jumped up in their imaging to what we had to do, you know, sort of 7, 8, 10 years ago to get the same thing.
Right. Well, you saw Gary Palmer's craft of how he image processes, what Gary does. He also teaches, amongst other things in our industry, he teaches people how to get the very best out of their astrophotography, how to use their equipment, to the best it can be used, and how to not only acquire images, but image process like he does, okay? And so you can really be put in the fast lane by taking one of his courses. I'm going to put down a link that's on the Explore Scientific website, but it does link back to Gary. It gives a little bit of background about him, and he was kind enough to do kind of a more lengthy interview with us to talk about the sun. So, but if you've seen more of Gary's work, his deep sky work is also mind-blowing. So, Gary, thank you very much, man. Thanks,
Thanks,
you.
Scott. Thank you.
Yep. Well, great. Okay, so we will move to Maxi Falaris. Maxi, thank you for coming on to Global Star Party tonight. And Maxi is also from Argentina. So we have 4 astronomers. I'm holding up 2 hands. That's 8. 4 astronomers from Argentina, which is amazing. So thank you, all you guys, for coming on and sharing all your knowledge and your passion with us from the Southern Hemisphere. Maxi, it's all yours, man.
Well, thank you, Scott. Hi, everyone. And well, thank you again for inviting me to this GSP. And for today, I want, first of all, say to you a good day of to bring the knowledge to everyone of the astronomy or space and everything. But well, tonight I think I'm going to be very shortly because, well, I didn't have too much time to do some pictures. But the last Friday I was invited for our friend Adrian Bradley, that he did the star party on the beach. I think that's what they call it. And I was maybe at this time with my equipment outside on my backyard, and I want to show to everyone some kinds of the objects that we have in the southern hemisphere that maybe is very low in the north, or maybe even it's impossible to see it. So we've been jumping with the go-to mount and doing some pictures about maybe 30 seconds with the camera. And I want to show you some pictures that I did that night that maybe well, it was very shortly because we were very excited to be maybe 47 Tucana, and then go to a galaxy, and then we tried to be in the Tarantula Nebula, but it was my house. Then we go to a sculptured galaxy, and then it was like we are jumping in a hyperspace point, like Star Wars, something like that. Because when you see the stars trading, it was some kind of that. Well, I want to share my screen. Okay, do you see it?
Yes.
Excellent. So before I start to do the little southern tour of the skies, I was taking pictures of a place that I showed before, of the Corona Australis. That's a region that we have very at the zenith here in this time of the year, and it has a very good place to watch and also take pictures. And well, I finally have my equipment established, because I could take a comma corrector F4, and finally I don't have that strangely stars, so I can start to do some very good pictures. Well, this is the stacked image. Maybe this was 12 minutes stacked, and this is a simulated straight to see how it looks like. This
Stunning.
This place is a global cluster, but also you have part of a dark nebula and have the reflection nebula from it. You can see the stars shining, and behind of that, the dust and the gas, the reflection that it has. Also, this place, it has some kind of that, but this isn't the focus. They are two stars very near from that. And also we have some galaxy, a very little one, very distant place. This almost at 500 light years from us, because in this place, let me. This was more up. Here in this place, they have the singularity of. I think that I read that is starting to create a new solar system. So it's I think it's the mostly solar system that is creating right now from very near from us. And well, this was a single picture, and then I only tried to flat it to get without the problems of the contamination, and to be very clean picture. But I think I will not going to edit this because it was only a few minutes, and they had it's very noisy. But the field of view that I had it is very amazing, because you have all in this place. You have a galaxy, you have nebula, you have a global cluster, you have double stars, you have a new solar system. It's all in a single picture, and this is good to well, in this case to share to everyone in a live view, because you can see this maybe in a single picture of 30 minutes, sorry, in 30 seconds, and it's able to show to everyone, even in a live view Facebook page, a YouTube page, or Twitch, or everywhere. The technology that we have today, it's amazing to encourage and show to all of the world practically what surrounds us. So then more later we went to a place in the constellation of Eridanus, that I went to the galaxy NGC 1365, I think they call it. And I do maybe in this picture 2 hours and a half pictures stacking. But I have only one single problem. The flats that I did, I think they have more dust, and when you see the picture, they are circles of that dust that is the focus. So this is all the field of view that I had it, and this is the only stacked picture that I did. But you can see this galaxy is very detailed. The core that it has, and also the arms, the spiral arms, and also the tiny galaxy that surround this place. You can see this little line from here. There is another one, and there are too many. Also, this place. This is in the constellation of Eridanus, or I don't remember, Eridanus or Fornax, Nico, if you're there.
I
I think it's in Fornax that.
Yeah,
In
that
Fornax,
looks like
right?
the Fornax galaxy.
Yeah,
Yes, it's in Fornax.
it's near
In
Fornax A. If I don't remember bad.
What a spectacular galaxy. It really
It-
is. So,
it's
so distinctive, you know.
well, this is the flatter
The barred
picture,
spiral. Yes.
and that I say the flat image screwed my image, but you know, I have all the spring season to start taking pictures of this place, and
And to clean the mirror.
no, the mirror, it wasn't. It was the
It was the corrector. That's in the corrector.
in the correct, exactly, because when I saw it today,
Yeah.
I see these little particles. So I say, oh God, okay, that's it.
Don't use brazo multiuso.
No. I have the perilla to
Yes, the
blow it,
brush.
and that's
Day
only.
rush. Day rush. Yeah.
And I really like the spikes of the stars. You know, this is very at the fringe of the image, and I even have these star trails, and the focus, I think it was okay. And then I also more later after is yes, after that star party, and I still of course taking pictures and trying the field of view of some places, and I went to the Horsehead Nebula, and then to M42, but then the clouds and the wet weather was a problem, because when I went to outside, I don't know, it was only a circle, a black circle. I saw the moon in surrounded by orange dust and mist, and it was now okay. That's it. Let's put again indoor. So this was the kind of picture that I was looking for, because I have too many galaxies, and I have to start practice with a lot of information, and to see the arms and the nebulosity of this galaxy. You know, I think this galaxy is almost 56 million light years.
Wow.
So practically the light of this galaxy is a little less from the extinction of the dinosaurs. So it's very, very old.
So all the small galaxies in the area must still be part of the Fornax group of galaxies, I would think.
I think yes, because more of this place, you have a very cluster galaxies. They are very near. I didn't went to that place because I was particularly searching this place for now. But I think in a couple days or weeks, I maybe we have a second chance. So I crop that area, and I try to process with what I got, and this is what I get of that image.
Wow!
Of course,
beautiful.
Looking very
amazing, Max.
If you go inside, you don't have maybe too much. Well, very maybe a poor processing, but the singularity and the spiral arms is able to see it, and I think I have to get a lot of information. I also remember from the distance that it is. And then, like I said, I went to M42, and this is only a single stack of 5 or 6, no, 6 pictures changing the gain of the camera, because the core of M42 was very brighting, and okay, I say no, let's get this and see what happened. So there was pictures of 3 minutes only at gain maybe 100 and then 50 and then 25 and then stacking, and this is what I get. This is all the field of view of the camera with the f4 telescope of 8 inches. Practically enter almost the M42 nebula, and the comma corrector will allow me to do the M41, the running nebula. So I only processed this place, I don't know, it was 5 a.m., 6 a.m., very, very quickly, and I was excited, and I get this of these images. Let me put it more bigger. You know, this place, this clouds, this gas of dust and clouds is amazing. The contrast that it has, you know, the gray particles, the more darkness, or then red, also the stars, the tiniest stars, and this brown nebulosity, and dark, because I think in this place behind it there are more stars that they are shining that nebulosity. So this place is amazing to start to practicing and also watch this nebulosity. This is a place that we see very good in the summer skies, but right now it's rising up at 3 a.m. And I think it was maybe 4 a.m. these pictures that I took. Then of course the clouds say go inside.
Good.
Yeah, I was in holidays in a few days that I had holidays, but I could rest. So well, I think this is the little the practicing of my equipment that I still working on, and of course it's a good the camera helps me to, of course, any camera. If you have a cell phone, you can show in a live view maybe the moon, maybe the planets in a Facebook page to show everyone that you have friends or maybe groups of astronomy and everything that what's up us in the sky. So well, I think that's it. Thank you.
Wonderful. Thank you
again.
Thank you, Maxi. That's great. Okay. Well, our last speaker was Cameron Gillis, but he had to bail out for due to another commitment. We can take a break and come back for after party, or how do you guys feel?
I'm going to be moving off now.
I would say so, Gary.
Yes.
It's very late for you.
4:15.
Yeah.
Come on.
Oh, come on.
I understand you.
I wouldn't mind if it was clear outside. Yeah, I'd still be here imaging. But
no, it's a great finale here.
So with that, I'm going to say thanks to everybody and goodbye. Yeah.
Thank you very much, Gary. Thank you.
Good night, Gary. Take care.
Excellent, excellent pictures, Gary.
Excellent tutorial, Gary. Excellent.
Thank you. Thank you.
Really.
All right.
Okay, guys, I will leave you too because
all right, Nicolas.
I need to wake up in a few hours.
Yes.
So have a great night, and thanks again, Scott.
Thank
and
you very
everyone
much. Thank you.
Thursday night.
Yeah, I want to thank
Take
everybody
care.
that was giving presentations. Mariano, thank you very much for being on Global Star Party. You are welcome to come back anytime, every time. So it's you have a home here. So that's great.
Thank you very much, Scott. I really enjoyed this experience. It was really nice. Thank you, everybody, for being here, and Cesar for introducing me into this really nice community.
Excelente presentación, Mariano. Un gusto, che.
Gracias, Maxi.
Okay. All right. I think we'll conclude the Global Star Party for tonight and let people get some rest. And we have a little feature video that I'll conclude with, and we will bid all of you a good night. Hopefully some of you out there have some clear skies and you're getting some observing in tonight as well. So thank you for watching. Thank you for presenting. And we'll be back next week with the Global Star Party 66. Now, this next Global Star Party happens on the date of the anniversary of the discovery of the Cepheid variable in the Andromeda Galaxy, when Edwin Hubble back in 1923, something like that, made this discovery. And so we will be talking about not only that discovery, but just discoveries in general and personal discoveries that we all make as amateur astronomers. I have my personal discovery of Saturn when I saw it for the first time. You know, it was a huge impact on me. So, thanks for watching. And Adrian, you check it in here with us?
Yes, I am.
Hi, Adrian.
Here's the man. Here's the man.
Yeah. I am here at a residence of one of our fellow lowbrow astronomers, and just dropped in to say hi. I saw some of the Global Star Party earlier. Maxie did an excellent job with our little astronomy at the beach presentation thing that we did. We had a good time, and people that joined enjoyed seeing some southern hemisphere objects they normally don't see here or up in Michigan. Right now I'm in Denver, Colorado. So this is late, but I'm on vacation, and it's actually earlier for me now. It's actually 9:17. So feels better feels better to be joining the Star Party at a reasonable hour for a change.
Right. That's right.
So
yeah.
So that works out.
This is one of our shorter Global Star Parties. We had a couple of people that could not make it that had would normally be here, but you know, we had a good Star Party anyways. You know, I look back at all the talks that we had with you know, Karim gave an excellent talk on distance scale. Mariano Poisson, who's still here with us, he is a you know, professional solar researcher, and he's working at the San Miguel Solar. Are you working at San Miguel Solar Observatory, or is it still being renovated, Mariano?
No. I'm working for an institute called Astronomy and Space Physics that is part of the National Agency for Research.
Okay. All right. That's great. That's great. Yeah, it was an honor to have you here. So,
I see Cesar.
And Cesar was here, still here. That's right.
Yes.
Mm-hmm.
I couldn't share with your Star Party because I was in our meeting, and I don't have the connection, because my idea was connect with you to your Star Party, but was not possible.
Well, it's okay. I mean, we didn't give a lot of
Maxi helped you a lot.
Maxi did very well. Yeah, we didn't have much going on this time at the Star Party. Last year, we actually had a few speakers, including David Levy, who he's a member of the Warren Astronomical Society, which is a part of our group. And we had him join in, give a talk. We had Brother Guy Consamano gave a talk. Dolores Hill gave a talk last year at our star party. This year it was just live views, and we had some solar viewing, and a couple different live views. We had someone handling the northern hemisphere for us, gentleman by the name of Doug Bach. Dr. Brian Adam did a presentation, and then Maxie had come on, and
the rooftop of my house. Sometimes.
Yeah. He imaged the Tarantula Nebula as soon as it rose, right over the rooftop of the neighbor's house. So the plans are still, we're still hoping to come down to Argentina, see it live.
Yeah,
that's the goal. But yeah, we'll be going a little early towards where Okie-Tex is held. We're going to camp out a day ahead. We're actually going to go near the end of this week.
Now, are you going to Black Mesa, or are you going to Camp Billy Joe?
We're going to start at Black Mesa.
Okay.
For a night, and then we're going to join the rest of our little crew at Camp Billy Joe.
Okay.
And we're going to get together as a group and go after some of those faint objects.
Oh, they're there. Yeah.
Yep. I plan to have a couple of pictures, mostly for posterity's sake, and to see what my newly modified Canon 6D is going to do. And then after that, it's mostly visual. I want to see mostly, get back to seeing it with the eyes.
The reality,
so much,
the feeling.
Yeah. And not so much trying to make the imager work or anything like that. If the electronics don't work, I'll star hop. There should be plenty of stars to star hop with.
You're going to be lost in the stars there. It is so dark. And it's a great facility. They have showers, of course. They've got a restaurant that's open most of the night. So you can go get a hamburger or whatever, something, to drink, some hot coffee if it's cold. You're up, was it about 4,000 feet there? Is that right?
Yeah, I think it is.
Right. So you're up high. It's dry. Skies are really transparent. You're far, far away from any city lights, and even the small towns that are nearby don't emit much light at all. So you're going to really enjoy it.
Yeah, that's what I'm looking forward to. If the rain forecasts aren't true, there are I think there's some cloudy days forecasted. As long as, couple is 9 days, and I registered for all 9. So, we're hoping for some good weather in at least 4 or 5 of those nights.
Right.
Have a good night, Mariano. I saw your chat. Okay,
good night.
Good night.
Mariano.
Good night, Mariano.
Mariano.
Right. Thank you, Mariano.
Yeah, so I'm hoping to enjoy the experience and hoping it's not going to be the last. So what I learned, the information I gathered from this experience, which is going to planning for the next event. So that will it'll be fun. I look forward to it. I'm going with quite a few fellow amateur astronomers from University Lowbrow Astronomers based out of the University of Michigan. And most of these guys have been going most of the years. They went back as early as 2012 and even I think 2009 for a couple of them. So I'll be leaning on their experience. I'll be watching out for the tarantulas and the tarantula eating wasps and everything else.
Oh yeah,
I've been warned about.
Yes.
And just hope to have a good time one way or another.
The last time I was at Okie-Tex, somebody was there's like a hill that goes up, and there's some sort of, they keep like some sort of toy or teddy bear or something up there at the top of this mountain that people go and walk out to. Okay. and it's right above, so you can look down on the Okie-Tex Star Party. It's a nice vantage point. But this guy went out, and you'll probably hear the story, and I may have it all wrong, but as I recall, the light was not. It was getting dark, and he misstepped, and I think he broke his ankle up there. So you want to be careful.
Yeah, I imagine this is as dark as it gets.
Yeah, there's no big hospitals around. Okay, so you know.
Yeah, so it's
bring your flashlight. Bring your flashlight, and if
we'll have
someone yells you because it's you are letting out safety first.
Yeah. Yeah, we'll definitely. I'll have to be careful. But yeah, so I'm looking forward to it. We'll see what happens. We packed the car and we drove. Took us 3 days, but we got this far, and then once we take off, a couple more days, we'll be out there. We'll start at Black Mesa, and the moon will still be setting, along with the sun. So we'll be, once it gets dark, we'll see what we can do. Yeah. Or it'll be rising late still. So
you have too much hours.
Yeah, yeah. That's the whole idea. This is the first time I've taken a vacation in a while, so I shouldn't have to work. Looking forward to just
you're gonna be working to go from one galaxy to the next.
Yeah, that's all I'll be working on.
Yeah, love it.
I'm looking forward to it. Now, Scott, you're going to be in Kansas City, right? I think.
I'm just doing a virtual talk, for Heart of America Star Parties. So doing that, and then I'm working with Night Sky Network, and they're working with NASA, and we'll be broadcasting, I guess, on some of not the main NASA channels, but some channels that NASA has, and so I'm looking forward to that. That's with Vivian White, and that'll be October 9th. So.
Okay, so the last day, if it's raining and we're all frustrated, then I'll have to tune in.
Tune in, yeah.
We won't have anything else.
Right.
We won't be observing, so we'll have to tune in. So, no, it sounds good.
I think you have a good chance. It's lots of clear nights, so just spirits up. It should be good. All right.
Looking forward to it. All righty. Well, I'm going to take off, but good seeing you all again. Glad to be invited. Next Tuesday, I don't know if I'll be able to be live on location, but I've done that before. So if I can drop in, if there's enough of a signal for me to be live on location, I may try that. So
yeah, it'll be a good test. It'll be a good test.
Yeah, we'll see what works.
What phone service are you using? Are you using AT&T?
I use AT&T, and I've heard AT&T is out there. So
yeah.
So I may be choppy. I may have to cut the video, but if I can hear and I can
you can tell us how it's going down for sure.
Yeah.
Yep.
Will do.
Very cool. Okay. All right.
All righty.
Thanks, everyone.
Sounds good.
Okay, I enjoy the view and blow your mind with those stars.
I'm looking forward to that. And even if it's cloudy, it'll probably blow my mind how dark it is.
Enjoy the nature, enjoy the peace.
Absolutely.
Yeah.
Yeah.
Cesar, thank you for the presentation that you gave with the Star Party and everything. It made me wish that I could have been there. That's a beautiful old Zeiss refractor that you were showing there.
Yeah.
And now, did that refractor come from the observatory complex that you're renovating?
Absolutely, yes.
I see.
Santiago Mayese could remove because the Air Force give him to use only the 2 days because the observatory is not yet for the major for the government, local government. The mayor visited us while we went we stayed in the fire, and because he's a very 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 friendly man, he's really interested, And when I tell him, because I tell about you in our Zoom on Tuesday, because it's not in everywhere in the world. It's not normal that a major is interested in something to recover about science, and he's personally interested to get this for the local government to have like an educational center. And this is very important because sometimes you need an own NG but when you have the local government interested to give to make a observatory work again, it's really great. It's a great, because they are working with the Air Force to trespass and get the key of the observatory for the local government. This is very important to start to work seriously in recovering and work in the process of recovering each instrument in that observatory. But it's a really huge economic effort, especially in Argentina. Politic things that is very important to show to the people that it's a real interest in science. But I think that we are in the right way about this. I really hope that it will be a great time to have something became returning to be something working again.
Yes. Well, it will just offer so much inspiration, for people that visit it, because they'll see the beautiful instruments, they'll see the science, they'll meet people like you that are doing educational outreach and, setting their, hearts on fire about science, so.
Absolutely. Maxi, you are invited to in October. I think that we can make another observatory party inside the observatory. To make something. Of course, Adrian too. If you like to come to Argentina, you know that.
Absolutely.
We say because of su casa.
I'm still trying to figure out how to justify the trip.
Also
you don't need only call to Maxi to me, and we can make the tour for you. No problem.
That sounds good. And it's Chivilcoy, right?
Yeah.
Which part?
Yes.
Yeah.
Yes, Buenos Aires, San Miguel is very near. Chivilcoy is only at 2 hours.
It's more to the west, but it may be 100 kilometers. Only 1 hour of travel.
Okay. That sounds
maybe
good.
2.
Yeah. Some friends are talking about going to Buenos Aires.
Yeah.
And how far is Chivilcoy from Buenos Aires?
2 hours driving. It's 200 kilometers.
We've just driven 3 days worth, so 2 hours.
As
long as we land.
No. For north to the south in Argentina is similar to east to the west in South America. Or in United States, going because it's 4,000 kilometers, 4,500 kilometers. It's a little less than west to coast United States.
Okay, so
we call it Ushuaia La Quiaca, the two cities.
That's easy for Adrian. No problem.
No problem.
That's what I do. I get up and
the roads are
6
single
hours,
roads
no problem.
mostly in Argentina, middle of freeways and tollways. Unfortunately, you need to pay. It's always on single
you
roads.
have to drive carefully.
Yes.
All right. Well, it sounds good. I'm going to go ahead.
All right, Adrian. Take care.
Oh, good seeing you. Good seeing you all.
Good night.
Take care, Adrian.
Nice.
See you.
Okay.
Yeah.
All right.
See
Maxie, Cesar, I'm going to let you guys go to bed. Okay. Maybe get something to eat or whatever. I'm going to get something to eat. And but thank you so much. So very much. And all right. And we will see you next week, hopefully. Okay. So take care.
So.
again, good night to the audience. Take care.
Good night, everyone.
Good night.
Galaxies once were regarded as island universes, isolated realms of gas, dust, and billions of stars that were separated by distances unimaginably vast.
But
There's
no
Maxi's
galaxy is an
galaxy.
island. In fact, galaxies prefer
Yeah.
company. The gravitational pull of a large, massive galaxy attracts like-sized and smaller neighbors. Galaxies may gather in modest groupings like these, or congregate by the hundreds in enormous clusters.
This is Abell 1689, one of the largest galaxy clusters known. This view spans some 2 million light years, or about the distance between our Milky Way galaxy and the nearest big spiral. Into this space, Abell 1689 packs more than 500 galaxies. As astronomers mapped nearby galaxy clusters, a more complete picture of cosmic structure emerged. Galaxy clusters gather in superclusters, and overlapping superclusters form chains and filaments spanning huge swaths of the sky. Welcome to the cosmic web. This all-sky map shows structures created by more than 1 million nearby galaxies.
Deeper studies show that this pattern continues to even greater distances. The cosmic web appears to be the backbone of our universe. The universe came into being 13.7 billion years ago. About 400,000 years later, it had cooled enough to form the first atoms. The event created a sudden pulse of light that astronomers now measure as the cosmic microwave background.
But then, the universe went dark. For millions of years.
Eventually, hydrogen gas cooled enough to collapse and form the first stars. These stars not only re-illuminated the universe, they became the seeds of all future cosmic structure.
The James Webb Space Telescope may be able to see clusters of these first stars. It may even catch a few of them dying in supernova explosions.
Either the first stars or their progeny gathered into the first galaxies. These were small, gas-rich dwarfs, nothing as grand as the big galaxies we see today, but they were the building blocks of modern galaxies.
As the dwarf galaxies form, collide, and merge into bigger galaxies, the cosmic web begins to take shape. With the James Webb Space Telescope, astronomers will glimpse the earliest phases of construction that led to the universe we know.
Finally tonight, a look at the really big picture, and to Elizabeth Farnsworth in San Francisco.
Today's issue of the journal Science reports new information about the evolution of the universe. It is apparently expanding faster now than it did in the past. That's the conclusion of new studies carried out by an international group of astronomers. A lead author of one of the studies was cosmologist Adam Rees of the University of California at Berkeley, and he joins us now. Thanks for being with us.
Thank you.
What is it that you learned?
Well, we've been using supernovae, which are exploding stars, and we've been using them as tools, as cosmological indicators of distance.
What do you mean using them?
Well, we'd like to map out the universe. We would like to see how fast it's expanding, but the universe is very dark. And occasionally a supernova explodes and it illuminates a piece of the universe. And while it's lit up, we can use that supernova to measure how fast that piece of the universe is rushing away from us.
And what if, so you're looking through the Hubble and other telescopes, right?
Right.
At these stars that are exploding billions of light years away.
That's right.
And then what do you do?
So what we've done is we've used these supernovae to measure how fast the universe is expanding today. And then we found some very distant supernovae, which are about 5 billion light years away. And it's taken the light so long to reach us that when it does reach us, it tells us how fast the universe is expanding when the light left the supernovae. So we can use this information to compare the expansion rate of the universe today to the expansion rate about 5 billion years ago.
And we should just remind people, a supernova, it's actually a star that is a huge, massive star is exploding.
It's a star which has reached the end of its life cycle and can no longer hold itself up under pressure and explodes.
Okay, so what are the conclusions you've drawn after looking at this information?
So our expectation was that the universe would continue to slow down after expanding. You see, there's gravity in the universe. Everything is pulling on everything else, all the stuff in there, the planets, the stars, and the galaxies. And we thought that this expansion would slow down. What we've actually found is a very strange result, that it's speeding up.
And this is, we should just go back to the beginning. This is all, the expansion originated with what people refer to as the Big Bang,
That's
right?
That's right.
And so you're finding it speeding up, and why?
That's a very good question. As I said, our naive expectation is gravity would cause it to slow down. And the less gravity we have, the less it would slow down. And yet, it should never really speed up unless there's some other force or some other sort of energy out there which is acting in the opposite direction of gravity. Now, Albert Einstein had suggested even back in the 1920s that there might be such a force. He called it his cosmological constant and described it as a repulsive force, something that goes in the opposite direction of gravity. So we're trying very hard to figure out what's going on with this data, but the implication seems to be that this cosmological constant, this repulsive force, might exist and might actually be pushing the universe out faster, overcoming gravity.
Why did some scientists react with what one called amazement and horror to these conclusions? Why was it such a shock to them, or to you?
Well, it's a very desperate scientist which relies on such outlandish sort of mechanisms to explain their data. So we were hoping we'd find a more simple explanation, something mundane. But
instead you found a new force in the universe?
Well, it would appear that way. We've gone down a long laundry list of other possibilities, and one by one we've checked them off. And from what we can see, there's really not too much left besides the possibility of this repulsive force.
Okay, now give us this in a little bit broader picture so that somebody who has no astronomical knowledge could understand it. How could you explain this in terms that would be easy for me to understand? Is there an analogy that you could use?
Well, I think the hardest thing for people to understand is what it's like when the universe expands. I guess a useful analogy would be if you had a loaf of raisin bread and it was rising in the oven, and it was getting bigger and doubling every so often, and you were just a raisin in the middle of the raisin bread. And that's us sitting in the Milky Way galaxy. All the other galaxies are the other raisins. And as the loaf of bread expands, all the other raisins appear to be rushing away from us. And it's interesting to try to measure at what rate this loaf is doubling in size. That's the expansion rate. You might expect it to just keep expanding at some certain rate, but what we found is the loaf is suddenly getting bigger and bigger at a great speed.
And does that mean that the universe could just keep on expanding forever?
Well, if you take this result at face value, if this is really true, the implication is, yes, that the universe would expand forever. And it also allows us to make a pretty good estimate of how old the universe is. We estimate using this technique, the universe is about 14 billion years old.
And that's older than had been thought, right?
That's right. And if this turns out to be true, it may be a relief to some cosmologists. There was a problem in cosmology known as the age crisis.
And remind us what cosmology is.
Cosmology is the study of the shape, structure, and dynamics of the universe.
Mm-hmm.
And there are some stars in the universe which are thought to be about 12 billion years old. And at one time, we thought the universe might only be 8 or 10 billion years old. So it was this kind of strange situation where it's like you're actually older than your mother, and that doesn't seem possible. If this cosmological constant exists, it will also represent a correction to the age of the universe and allow it to be older than some of the oldest objects in it, which doesn't mean this is true, doesn't mean it's right, but it sure would be a relief.
Is there a lot of skepticism still about these findings among scientists?
Oh, yes, I would say so. And I would say that we're very skeptical, too. As I said, we'd like to find a more mundane explanation for it. But I think if this isn't right, it's probably something equally as interesting.
What do you say to somebody who says, why should I care about this? You know, I'm sitting here, I can see the stars, they look great. Why do I care about whether it's expanding quicker now or whether it's going to end with a bang or a whimper?
Well, I think people have always been very curious about space and the universe. I think our everyday experience is we look up and we see all the stars and they just look frozen there. And we would expect the universe is just static. But to learn the universe is actually dynamic. It has a history, it has a start, it has a future. And I think once we come to understand that, we want to know the answers to these questions. When did it start? Why did it start? Where's it going? What's the ultimate fate?
And finally, in the few seconds we have left, what kind of studies will end some of the skepticism? Do you have studies underway now?
There are other groups which have worked to confirm this result, and they have actually confirmed it from this experiment. But as we often find in science, it may take a completely different experiment, something which has a whole other set of assumptions to confirm this. Probably in about 10 years, scientists are going to be studying the cosmic microwave background, which is the radiation left over from the Big Bang. And there may be clues in that as to whether there really is this repulsive force.
Okay, well, Adam Rees, thank you very much.
Thank you.
Why do we chase this thing? Jumping from one continent to the next, just to bathe for a moment in the absence of light? Who are we? What are we searching for?
T.S. Eliot wrote, "We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time."
One of the qualities of seeing an eclipse is it makes you understand that every given thing is in a particular patterned relation with every other thing.
It gives me a sense of scale, gives me a sense of where I fit into the universe.
It is art, is poetry, it's this kind of experience of going and seeing totality in which what feels merely metaphorical is suddenly experiential encounter.
Immediately afterwards, you have that overwhelming desire to see another one. That's the moment an eclipse chaser is born.
These are folks who are running all over the world for this event that lasts all of 2 or 3 minutes. Who are these people?
It's unique each time. And therefore that freshness, even if we've seen it over and over again, oh my gosh, it has the potential to re-inspire us.
A total eclipse of the sun doesn't just unfold in the heavens. It transforms the minds and hearts of those who experience it firsthand. The same is true of journeys to the most remote regions of our planet. Whether we're standing on a mountain peak or in a stark polar landscape, we can't help but reflect on our place within the larger scheme of things.